Hello there, and welcome to Science for Sleep, a place where curiosity slows down, where science takes its time, and where big ideas are allowed to unfold gently without urgency. Tonight, we're exploring a question that lives far beyond everyday experience, yet quietly touches the deepest structure of reality itself. We're going to talk about pressure, not the kind you feel in a busy week or a ringing deadline, but physical pressure, taken to its most extreme imaginable limit. Specifically, what really happens when pressure reaches the Planck scale. That phrase alone can sound intimidating or distant, or like something that belongs only in chalk-covered lecture halls. But we'll approach it differently here. Slowly, carefully, with room to breathe. Because even the most extreme ideas in physics often begin with very familiar sensations. Pressure, after all, is something you've known your whole life. You've felt it when you press your hand into a mattress and watch the fabric dip. You've noticed it in your ears as an airplane climbs. You've experienced it when opening a tightly sealed jar, or when diving just a little deeper into a swimming pool. Pressure is simply force spread over an area. A quiet, persistent push. And most of the time, it behaves politely. It follows rules that feel intuitive. Push harder, and things compress a bit more. Apply pressure evenly, and materials respond predictably. But the universe, as it turns out, has a breaking point for intuition, and somewhere far beyond anything we can recreate directly, pressure stops being a simple squeeze and starts becoming something far stranger. Before we wander too far into that territory, take a moment to notice where you are right now. Are you listening from a bedroom, a couch, maybe a dimly lit room where the day has already loosened its grip? What time is it where you are? Is it late evening, edging towards sleep, or early morning with the rest of the world still quiet? There's something fitting about thinking of extreme physics while the outside world slows down. The universe does some of its most interesting work in silence. If you find this kind of exploration soothing, or if it helps your thoughts settle into a slower rhythm, you're always welcome to like the video or subscribe. It helps this calm corner reach others who might need a place where questions don't demand immediate answers. No rush, no pressure, quite the opposite really. Now, when physicists talk about the Planck scale, they aren't referring to a place you could visit or a machine you could point to. It's not a location in space, it's a regime, a set of conditions where the familiar laws of physics stop cooperating with one another. The Planck scale shows up when quantities like length, time, energy, and pressure reach values so extreme that gravity and quantum mechanics collide, often uncomfortably. Pressure at the Planck scale is not just very high, it's unimaginably high. So high that the words we usually rely on start to lose their usefulness. To give a sense of scale, without slipping into abstraction, imagine compressing matter more tightly than the core of any star, more tightly than the interior of a neutron star, more tightly than anything known to exist in the present universe. Imagine continuing to compress even when there seems to be nothing left to give. At ordinary pressures, atoms respond by moving closer together. The spaces between them shrink. Electron clouds overlap a bit more. Materials stiffen, warm, sometimes crack or melt. Under greater pressures, atoms begin to distort. Electrons are forced into higher energy states. Chemical bonds change their behavior. Elements that are gases at room temperature become metallic solids. Hydrogen, the simplest and most abundant element in the universe, begins to act in ways that barely resemble its everyday form. But even these exotic states still belong to a realm where atoms exist as atoms, where nuclei remain distinct, where space, though compressed, still behaves like space. As pressure increases further, those assumptions begin to fail. Inside massive stars, gravity provides an ongoing source of compression. When a star runs out of fuel, it loses the outward pressure needed to counteract its own weight. What follows depends on the star's mass. Smaller stars collapse into white dwarfs, where electron pressure holds things up. Larger ones collapse further, squeezing matter until electrons are forced into protons, creating neutrons. The result is a neutron star, an object so dense that a teaspoon of its material would outweigh a mountain. Neutron stars already challenge our understanding of pressure. They are supported not by heat or fusion, but by quantum mechanical effects that resist further compression. Neutron degeneracy pressure arises because neutrons, like all fermions, refuse to occupy the same quantum state. It's a quiet but absolute rule. You cannot squeeze them arbitrarily close without consequence. And yet, even neutron degeneracy pressure has its limits. Add enough mass, and gravity continues its work. What happens next is where certainty starts to fray. Matter may collapse into something even more compact. The equations become harder to solve. Observations grow indirect. Pressure, in this regime, becomes less about pushing particles together and more about confronting the structure of spacetime itself. The Planck scale sits at the edge of this confrontation. It is defined using three fundamental constants: the speed of light, Planck's constant, and the gravitational constant. Combine them in just the right way, and you arrive at natural units that describe the smallest meaningful lengths, shortest meaningful times, and highest meaningful energies we know how to talk about. Planck pressure emerges from these same ingredients. It represents a pressure so intense that spacetime is expected to fluctuate violently, no longer smooth or continuous. At this scale, the idea of squeezing matter becomes secondary. Pressure is no longer acting only on particles. It is acting on the geometry of reality. Space may no longer behave like a stable stage. Time may lose its familiar order. Distances might blur. Cause and effect might not line up cleanly. The usual mental images of compression simply stop applying. What's important to understand is that we are not certain what actually happens at this limit. The Planck scale is a boundary of knowledge, not a catalogue of answers. Our best theories, general relativity and quantum mechanics, both work extraordinarily well in their own domains. But when pressure reaches Planck levels, they speak different languages. Gravity demands smooth curves and continuous geometry. Quantum mechanics insists on uncertainty, discreteness, and probability. So when pressure rises toward this extreme, we don't yet have a single, unified description of events. Instead, we have clues, mathematical hints, partial models, thought experiments that gesture toward possibilities without fully settling on one story. Some approaches suggest spacetime becomes grainy, composed of tiny units. Others propose that space and time dissolve into something more abstract, like networks of relationships or vibrating structures. Still others hint that pressure itself might cease to be a meaningful concept. This uncertainty is not a failure. It's a sign that we're approaching a frontier. Physics has always advanced by finding the edges where old ideas stop working. Pressure at the Planck scale represents one of those edges. It's where compression, gravity, energy, and quantum behavior converge so tightly that separating them becomes impossible. As we continue, we'll begin closer to home, looking carefully at how pressure behaves before it becomes extreme, not because the everyday case is trivial, but because it lays the groundwork for everything that follows. The journey toward the Planck scale doesn't begin with cosmic violence. It begins with simple compression, familiar rules, and a gradual tightening of possibilities that leads us step by step into stranger territory. Pressure is one of those ideas that feels almost too ordinary to deserve deep attention, at least at first. It shows up quietly in daily life, doing its job without much ceremony. You lean your head into a pillow and it yields just enough to be comfortable. You press your fingers into soft dough and leave shallow impressions behind. You step onto wet sand and feel it firm up beneath your weight. None of this feels mysterious. It feels intuitive, even reassuring, as though the world is responding politely to your presence. At its simplest, pressure is force distributed over an area. That definition is neat, compact, and accurate, but it hides how widely pressure operates across scales. When you lie down on a bed, your weight is spread out, so the pressure on any one point is relatively small. Stand on one foot and the pressure increases. Stand on the tip of a toe and it increases further. The force hasn't changed much, but the area has, and the material beneath you responds accordingly. Mattresses compress, floors resist, bones and muscles quietly coordinate to keep everything stable. Liquids and gases experience pressure too, though in ways that feel less solid. When you dive underwater, pressure builds steadily as you go deeper. Your ears notice first, because air-filled spaces are especially sensitive to compression. Every additional meter adds more water above you, and that water has weight. It presses down, not dramatically but persistently. The deeper you go, the more that pressure accumulates. Fish that live at great depths are adapted to this constant squeeze. Their bodies are structured to match the surrounding pressure so that nothing inside them is trying to expand or collapse unexpectedly. In the atmosphere, pressure works in reverse. At sea level, the air above you weighs about 10 tons per square meter. You don't feel it because the pressure inside your body balances it almost perfectly. As you climb higher, there's less air above you. The pressure drops, breathing becomes harder, water boils at lower temperatures. Eventually, without protection, the environment becomes incompatible with human physiology. Pressure, in this sense, is one of the quiet conditions that makes life on Earth possible at all. So far, pressure behaves predictably. Increase it and materials compress. Decrease it and they expand. Solids resist more than liquids. Liquids resist more than gases, and gases respond readily by changing volume. These differences arise from how tightly particles are bound together. In gases, particles move freely and occupy whatever space is available. In liquids, they are closer and interact more strongly. In solids, they are locked into structured arrangements, resisting deformation unless sufficient force is applied. Even within this familiar range, pressure can produce surprising effects. Carbon, for example, rearranges itself under pressure. At everyday conditions, it forms graphite, soft and slippery. Apply immense pressure deep within the Earth, and the same carbon atoms snap into the rigid lattice of diamond. The chemistry doesn't change. The atoms don't become different elements. Only the pressure changes, and with it, the structure. This sensitivity to pressure hints at something deeper. Matter is not static. It responds, adapts, reorganizes. Pressure is one of the ways the universe nudges matter into new configurations. On Earth, this happens slowly, over geological timescales, shaping rocks, forming minerals, and driving tectonic processes. In laboratories, scientists replicate higher pressures using devices like diamond anvil cells, squeezing tiny samples between ultra-hard surfaces to observe how materials behave when space becomes scarce. As pressure increases beyond everyday experience, matter starts to act less like the solid objects we recognize and more like a collection of interacting quantum systems. Atoms are no longer comfortably spaced. Electron clouds overlap significantly. Energy levels shift. Electrical conductivity changes. Some materials that are insulators at normal pressure become conductors, or even superconductors when squeezed hard enough. Still, even here, atoms remain atoms. Their nuclei stay intact. Electrons still orbit in recognizable patterns, even if those patterns are distorted. To reach truly extreme pressures, you need more than mechanical squeezing. You need gravity. Gravity is nature's most persistent compressor. It never switches off. It acts across vast distances and accumulates its effects over time. When enough mass gathers in one place, gravity pulls everything inward, steadily increasing pressure at the center. This is how planets form, how stars ignite, and how entire galaxies take shape. Consider Earth. Its core exists under pressures millions of times greater than atmospheric pressure. Iron there behaves differently than iron on the surface. It flows slowly over long time scales, generating Earth's magnetic field. Move outward, and pressure decreases layer by layer. Crust, mantle, core. Each region reflects a balance between gravitational compression and the material's resistance to being squeezed further. Stars take this process much further. In the Sun, pressure at the core is high enough to force hydrogen nuclei close together despite their electrical repulsion. This allows nuclear fusion to occur, releasing energy that pushes outward and balances gravity's inward pull. The star exists in a delicate equilibrium. Pressure is not just a passive condition, it is an active participant in the star's life. When a star exhausts its fuel, that balance changes. Without the outward pressure from fusion, gravity gains the upper hand. The star begins to collapse. As it does, pressure rises dramatically, and new forms of resistance emerge. First, electrons resist being squeezed into the same states. If the star is small enough, this electron degeneracy pressure halts the collapse, leaving behind a white dwarf. If the star is more massive, gravity overwhelms electron resistance. Electrons are forced into protons, creating neutrons. The collapse continues until neutron degeneracy pressure takes over. The result is neutron star, an object supported by one of the strongest known forms of pressure, arising purely from quantum mechanical rules rather than thermal motion. Up to this point, pressure has always had something to push back with. Atoms, electrons, neutrons. Each layer of matter introduces a new form of stiffness, a new refusal to be compressed further. These refusals are not based on strength in the everyday sense. They arise from fundamental principles, like the Pauli exclusion principle, which dictates how certain particles are allowed to exist. What makes pressure such a powerful concept is that it reveals these principles gradually. As pressure increases, it strips away layers of structure. Molecules give way to atoms. Atoms give way to nuclei and electrons. Electrons give way to neutrons. Each transition exposes a deeper level of reality. This gradual stripping is why starting with pillows and planets matters. Pressure does not leap suddenly from soft cushions to cosmic extremes. It climbs, it accumulates. It pushes matter through a sequence of responses, each one logical within its own domain. The unfamiliar behavior at high pressure is not arbitrary. It is the natural continuation of rules that were already present at lower levels. What changes as pressure increases is which rules dominate. At low pressure, chemistry rules. At moderate pressure, condensed matter physics takes the lead. At stellar pressures, nuclear physics enters the scene. And as pressure climbs toward its ultimate limits, gravity and quantum mechanics begin to overlap in ways we do not yet fully understand. At every stage, pressure is telling us how crowded reality has become. It measures how much resistance space itself offers to being occupied. At ordinary scales, space is generous. There is room for atoms to arrange themselves comfortably. At extreme scales, space becomes scarce. The universe starts negotiating with itself over what is allowed to exist and in what form. When people hear the phrase extreme pressure, it's easy to assume it simply means more of the same thing, turned up to an uncomfortable level, as though pressure were a volume knob that you keep twisting until the sound becomes unbearable. In everyday life, that assumption works well enough. A little pressure dents foam, more pressure cracks ice, enough pressure bends metal or shatters stone. Each step feels like a continuation of the last. Stronger squeeze, stronger response. But in physics, the word extreme does not merely describe intensity. It marks a transition point, a place where familiar behavior stops scaling smoothly and something qualitatively different begins to happen. Extreme pressure is not just high pressure. It is pressure that forces matter to abandon the rules it was following before and adopt entirely new ones. To understand what that really means, it helps to pause and think about what pressure is actually measuring. Pressure tells us how much force is being applied to a given area, but more importantly, it tells us how crowded reality has become at that location. It is a measure of how little room things have left. At low pressure, particles have space to move, adjust and rearrange themselves gently. At higher pressure, their freedom shrinks. Paths close off, options disappear, interactions that were once negligible become unavoidable. In your daily experience, extreme pressure might mean something like standing at the bottom of a deep pool, where the water presses firmly against your body. Or it might mean a heavy object resting on your foot, enough to hurt, but not enough to cause real damage. Even the pressures involved in industrial machinery or deep sea exploration, impressive as they are, still operate within a regime where atoms remain comfortably intact and space behaves predictably. Physics, however, stretches the word extreme far beyond those boundaries. Extreme pressure, in a scientific sense, begins where matter is forced into arrangements that cannot exist under ordinary conditions. It's where the internal structure of atoms becomes unstable, where electrons are no longer able to occupy their usual roles, and where forces that are normally secondary take center stage. One useful way to think about this is to imagine pressure as a conversation between matter and space. At low pressure, space is generous. It allows matter to spread out, vibrate, and organize itself in complex but forgiving ways. Molecules can form, crystals can grow, life can exist. As pressure increases, space becomes less accommodating. It begins asking matter to justify every bit of room it occupies. At moderate pressures, matter responds by rearranging. Molecules shift closer together. Solids become denser. Chemical bonds bend and sometimes break, only to reform in new configurations. These changes are often reversible. Release the pressure and the material relaxes back into its original state. Nothing fundamental has been lost. Extreme pressure, by contrast, crosses thresholds where reversibility fails. At these levels, matter is not just rearranged, it is transformed. The identities of particles remain the same, but their relationships do not. Electrons can no longer orbit nuclei in the familiar way. Energy levels compress. Quantum effects that are usually subtle become dominant. To see why this matters, consider how atoms normally work. An atom is mostly empty space. The nucleus occupies a tiny central region, while electrons exist as probability clouds spread over a relatively large volume. These clouds repel one another due to their negative charge, which helps keep atoms from collapsing into each other under normal conditions. Pressure, in effect, tries to shrink that empty space. At first, electrons resist gently. They move into slightly higher energy states. Orbitals distort. Atoms pack closer together. But electrons are governed by strict quantum rules. They cannot all pile into the same state. As pressure increases, these rules become increasingly restrictive. Eventually, electrons are forced into configurations that cost enormous amounts of energy. This is one of the first markers of truly extreme pressure. When adding a bit more compression suddenly requires a disproportionate increase in energy, you know you're pushing against a fundamental limit. The system is no longer responding smoothly. It is fighting back. In white dwarfs, this fight becomes dramatic. These stellar remnants are supported not by heat, but by electron degeneracy pressure. The electrons are packed so tightly that quantum mechanics itself provides the resistance. No classical force is pushing outward. Instead, the exclusion principle forbids electrons from occupying identical states, and that prohibition manifests as pressure. Calling this pressure extreme is not poetic exaggeration. The densities involved are staggering. A cubic centimetre of white dwarf material weighs tons. Yet even here, matter still has structure. Nuclei remain distinct. Space, though cramped, still exists as something separable from matter. Push further, and the meaning of extreme shifts again. When gravity overwhelms electron degeneracy pressure, electrons are forced into protons, creating neutrons. This is not a chemical reaction. It is a fundamental restructuring of matter. The resulting neutron-rich material behaves nothing like anything found on Earth. Neutron degeneracy pressure is even more extreme than its electronic counterpart. It arises from the same quantum principles but applies to much heavier particles. The distances between particles shrink further. The energies involved rise. The distinction between individual nuclei begins to blur. Neutron stars are essentially giant atomic nuclei, held together by gravity and quantum rules in uneasy cooperation. At this stage, extreme pressure has erased entire categories of familiar physics. Chemistry is gone, atomic structure is gone. Even the idea of solid versus liquid becomes ambiguous. Matter exists in a state that defies everyday classification, and yet, from a physicist's perspective, this still may not qualify as the most extreme pressure possible. Because even neutron degeneracy pressure has a limit. It is incredibly strong, but it is not infinite. Given enough mass, gravity can overwhelm it too. When that happens, pressure stops being something that matter alone can supply. Resistance must come from somewhere else, or collapse continues unchecked. This is where extreme pressure begins to merge with questions about spacetime itself. At very high densities, pressure contributes significantly to gravity. In general relativity, pressure is not just a response to gravity. It is a source of gravity. This is a subtle but profound point. High pressure increases the curvature of spacetime, which in turn enhances gravitational collapse. At extreme levels, pressure no longer acts as a simple counterforce. It becomes part of the problem it is trying to solve. This feedback loop is one of the reasons the word extreme carries so much weight in this context. At everyday levels, pressure stabilizes systems. It prevents collapse. At ultra-high levels, pressure can accelerate collapse. The same concept changes role depending on scale. As we approach the Planck regime, extreme pressure ceases to be something we can describe purely in terms of matter being squeezed. The densities involved imply energy so high that quantum fluctuations of spacetime itself become unavoidable. Space is no longer a smooth backdrop. It is expected to jitter, fluctuate, and possibly fragment into something more granular. At this point, pressure may no longer be a well-defined quantity in the way we usually mean it. Pressure assumes that you can define an area over which force is applied. It assumes that space can be divided cleanly into regions. At Planck scales, those assumptions may fail. Distances approach the smallest meaningful length. Time intervals approach the smallest meaningful duration. The idea of area itself becomes fuzzy. So when physicists talk about extreme pressure near the Planck scale, they are often speaking cautiously. They are extrapolating from known equations into a regime where those equations are not guaranteed to apply. Extreme pressure here is a signpost, not a destination. It marks where our current understanding begins to lose coherence. What makes this especially interesting is that extreme pressure is not just about violence or destruction. It is about limits. It tells us where our concepts stop working. It exposes the assumptions we didn't realize we were making. For example, we assume that space exists independently of what occupies it. Extreme pressure challenges that. We assume that matter can always be described as particles. Extreme pressure challenges that too. In this sense, extreme pressure is a diagnostic tool. It reveals the architecture of physical law by stressing it until cracks appear. Those cracks are not failures. They are invitations to deeper understanding. It's also worth noting that extreme pressure is not something the universe seeks out casually. These conditions are rare. They appear in the cores of massive stars, in the aftermath of stellar collapse, and possibly at the very beginning of the universe. They are not part of the everyday cosmic background. They are special, transient, or localized. That rarity matters because it suggests that extreme pressure is not just another state of matter, but a boundary condition for reality itself. It defines what is possible, not what is common. And boundaries, in physics, are often where the most important insights lie. Extreme pressure is not just a stronger squeeze. It is pressure that forces the universe to reveal which rules are negotiable and which are not. Matter behaves politely when it has room. It spreads out when warmed, contracts when cooled, and rearranges itself in ways that feel cooperative. Solids resist shape changes. Liquids flow around obstacles. Gases expand to fill whatever space they are given. All of this relies on one quiet assumption that we almost never question. There is space available. Space to move into, space to vibrate within, space to exist without constant interference from neighbouring particles. When matter can no longer breathe, that assumption collapses. Breathing in this context has nothing to do with oxygen or lungs. It refers to freedom. The freedom of particles to occupy different positions, to adjust their energy levels, to respond gradually rather than abruptly. When pressure becomes intense enough, matter loses that freedom. Every particle begins to feel the presence of every other particle all the time. There is no slack left in the system, no empty room to retreat into. At low pressure, atoms are separated by distances far larger than their nuclei. Even in solids, where atoms are packed tightly by everyday standards, the actual cores of atoms are still extraordinarily far apart compared to their size. Most of what we call solid matter is empty space stabilized by electromagnetic forces and quantum rules. This emptiness is what allows materials to flex, absorb shocks, and exist in stable forms. As pressure increases, that emptiness shrinks. At first, the changes are subtle. Atoms move closer together. Electron clouds begin to overlap slightly. Vibrations become constrained. The material stiffens. In metals, electrical properties change because electrons are shared more freely. In insulators, band gaps narrow. These effects are noticeable but not catastrophic. Matter is adjusting, not breaking. Eventually, however, a tipping point is reached. The electrons surrounding atomic nuclei begin to feel crowded. They are forced into higher energy states, not because energy is being added directly, but because lower states are no longer available. This is a purely quantum effect. The Pauli exclusion principle states that no two identical fermions can occupy the same quantum state simultaneously. Electrons obey this rule absolutely. When pressure rises enough that available quantum states fill up, electrons have nowhere to go but up the energy ladder. This increase in energy manifests as resistance to further compression. Matter begins to push back not because of heat or chemical bonding, but because quantum mechanics forbids certain arrangements. This is the first stage where matter truly struggles to breathe. In everyday materials, this resistance shows up as hardness. Diamond, for example, is hard because its carbon atoms are arranged in a rigid lattice that leaves little room for deformation. But even diamond relies on electron structures that assume space exists between nuclei. Under extreme pressure, even diamond strength becomes irrelevant. Hardness is a macroscopic property. Extreme pressure operates at a microscopic and then submicroscopic level. As compression continues, electron degeneracy pressure becomes dominant. This is not a force in the classical sense. Nothing is pushing outward in a mechanical way. Instead, the resistance arises because the electrons simply cannot all be placed into lower energy states. The universe refuses to allow that configuration. In white dwarf stars, this refusal is what prevents total collapse. The star has exhausted its nuclear fuel. There is no fusion generating outward pressure. Gravity pulls relentlessly inward. Matter is squeezed until electron degeneracy pressure halts the collapse. The star stabilizes in a state where matter is unimaginably dense but still structured. At this point, matter has very little room left to breathe. The distances between nuclei are drastically reduced. Electron motion is highly constrained. Thermal motion becomes almost irrelevant compared to quantum effects. Temperature, which normally measures how vigorously particles move, loses much of its influence. Even at relatively low temperatures, the pressure remains immense because it is no longer tied to heat. If mass increases further, gravity does not stop negotiating. It continues to demand more compression. Electron degeneracy pressure, strong as it is, has a limit. When that limit is exceeded, the system finds a new way to reduce its energy. Electrons are forced into protons. This is not something that happens casually. Under normal conditions, protons and electrons coexist peacefully, separated by electromagnetic forces. Forcing them together requires extreme pressure and energy. When it happens, the result is neutron formation. Protons capture electrons, producing neutrons and neutrinos. The neutrinos escape, carrying away energy. What remains is matter composed largely of neutrons. At this stage, matter has lost almost all resemblance to anything familiar. There are no atoms, no electron clouds, no chemistry. The distinction between individual nuclei fades. Matter becomes a dense, neutron-rich substance governed by nuclear forces and quantum rules. Neutron degeneracy pressure now takes over the role previously played by electrons. Neutrons, like electrons, are fermions. They obey the exclusion principle. They resist being squeezed into identical states. This resistance can hold up an entire star against gravitational collapse, forming a neutron star. Here, matter is packed so tightly that a single teaspoon would outweigh a mountain. The interior pressure is staggering. Yet even here, matter still exists as matter. Neutrons retain identity. Nuclear forces provide structure. Space, though severely compressed, has not vanished. But breathing room is almost entirely gone. Inside a neutron star, particles are in constant close contact. Motion is highly restricted. The system is locked into an extreme configuration where even slight changes in mass or pressure can have dramatic consequences. The star exists on a knife edge between stability and further collapse. This brings us to a crucial idea. When matter can no longer breathe, its behavior becomes dominated by rules that are invisible at lower pressures. Quantum statistics, nuclear interactions, and relativistic effects take precedence. Familiar concepts like solidity, temperature, and even particle identity begin to blur. Pressure at this level is not merely squeezing matter, it is redefining what matter is allowed to be. As pressure continues to rise beyond neutron degeneracy, the situation becomes increasingly uncertain. Theoretical models suggest various possibilities. Neutrons themselves may break down into more exotic forms. Quark matter may form, where quarks are no longer confined within individual neutrons. Strange matter, involving strange quarks, may appear. These are not poetic ideas. They are serious proposals grounded in quantum chromodynamics, the theory describing the strong nuclear force. In these states, matter is compressed so tightly that even the concept of a neutron as a distinct particle becomes questionable. Quarks, which are usually confined inside protons and neutrons, may move more freely in a dense sea. The system behaves less like a collection of particles and more like a continuous quantum medium. Breathing room is effectively zero. At this point, pressure is no longer acting on atoms or nuclei. It is acting on fundamental degrees of freedom. The resistance to compression comes from the deepest layers of physical law we currently understand. Yet even these layers may not be the final ones. As densities climb toward those associated with the Planck scale, gravity itself becomes inseparable from quantum behavior. Spacetime curvature becomes extreme. Energy densities approach levels where quantum fluctuations of spacetime are expected to become significant. The idea of particles existing within space begins to lose meaning, because space itself may no longer be well defined. When matter cannot breathe at all, it may no longer be accurate to describe it as matter in the traditional sense. It becomes a region where energy, geometry, and quantum uncertainty intertwine. Pressure here is not just resistance, it is a symptom of deeper conflicts between the laws governing the universe. One of the most unsettling aspects of this regime is that pressure may stop behaving as a stabilizing factor altogether. In general relativity, pressure contributes to gravitational attraction. At extreme levels, increasing pressure can actually increase the tendency to collapse. The very thing that once resisted compression now accelerates it. This reversal challenges intuition deeply. It means that beyond a certain point, there is no amount of internal resistance that can halt collapse. The system enters a runaway state. According to classical general relativity, this leads to singularities, points where density and pressure become infinite and the equations break down. Whether such singularities truly exist, or whether quantum gravity intervenes to prevent them, remains unknown. What is clear is that when matter can no longer breathe, we're no longer dealing with ordinary physical systems. We are probing the limits of description itself. What makes this progression remarkable is its continuity. There is no single moment where matter suddenly stops breathing. Instead, freedom is lost gradually. First electrons lose room, then nuclei lose distinction, then particles themselves may lose identity. Each stage is a response to increasing pressure, each governed by deeper and more restrictive rules. This gradual tightening is why pressure is such a powerful probe of reality. It reveals the hierarchy of constraints that structure the universe. It shows which freedoms are superficial and which are fundamental. The collapse from atoms to nuclei does not arrive with an explosion or a dramatic tearing apart of matter. It happens quietly, steadily, almost politely, as pressure increases and the familiar scaffolding of structure gives way piece by piece. There is no single moment where atoms announce their departure. Instead, their defining features gradually lose relevance, until what remains no longer fits the name at all. At ordinary pressures, atoms are stable arrangements. A dense, compact nucleus sits at the centre, surrounded by electrons that occupy well-defined quantum states. These electrons are not tiny planets orbiting a sun, but they still form layered regions, shells and orbitals that determine how atoms interact, bond, and build the complexity of chemistry. The atom, as a unit, is extraordinarily resilient under everyday conditions. You can heat it, cool it, shake it, bind it, or dissolve it, and it remains recognizably an atom. Pressure begins to change that stability long before it destroys it. As atoms are pushed closer together, their electron clouds begin to overlap. At first, this overlap is mild. It alters bonding behavior, conductivity, and rigidity, but the atom itself remains intact. This is the regime of high-pressure chemistry and condensed matter physics, where materials behave in surprising but still recognizable ways. Elements change phases, insulators become metals, crystalline structures rearrange. None of this threatens the existence of the nucleus. What pressure is really doing at this stage is erasing the empty space atoms rely on. The vast majority of an atom's volume is empty. That emptiness is not optional, it is essential. It allows electrons to occupy low-energy states without colliding, and it allows electromagnetic forces to balance cleanly. Pressure steadily removes that emptiness. As compression continues, electrons are forced into higher and higher energy states. This is not because heat is being added, but because lower states are becoming unavailable. The exclusion principle enforces this strictly. You cannot push electrons into the same configuration without paying an energy cost. That cost rises sharply as pressure increases. Eventually, electrons are no longer primarily associated with individual atoms. Instead of belonging to specific nuclei, they form a dense shared sea. This is already familiar in metals, but under extreme pressure, it becomes unavoidable for all matter. Atomic identity begins to blur. The idea of distinct atoms loses meaning because electrons no longer mark boundaries between them. At this point, atoms still exist in name, but not in function. They no longer behave as independent units. Chemistry fades away. What remains is a dense assembly of nuclei immersed in a highly constrained electron environment. This transition is quiet, because it is driven by necessity rather than instability. Nothing is exploding. Nothing is violently rearranging. The system is simply following the lowest energy path available under increasing pressure. Each step removes another degree of freedom. As pressure rises further, even this arrangement becomes energetically unfavourable. The electrons, now squeezed into extreme confinement, carry enormous energy. The system looks for a way to reduce that energy. The solution is not to push electrons harder, but to remove them from the problem altogether. This is where the collapse from atoms to nuclei becomes literal. Under sufficiently extreme pressure, electrons are forced into direct contact with protons inside atomic nuclei. When this happens, a process called electron capture occurs. A proton absorbs an electron and transforms into a neutron, emitting a neutrino in the process. The neutrino escapes, carrying away energy. What remains is a nucleus with fewer protons and more neutrons. This is not chemistry. It is nuclear transformation driven by pressure alone. As electron capture proceeds throughout the material, atoms lose their defining charge balance. The distinction between elements becomes irrelevant. Carbon, oxygen, iron all begin to converge toward a similar neutron-rich state. Atomic number no longer matters. What matters is density and pressure. At this stage, matter is no longer composed of atoms at all. It is composed of nuclei packed so tightly that electrons cannot exist independently. The structure of matter has simplified dramatically. Complexity has been stripped away. The collapse continues, not because something has gone wrong, but because gravity insists. In massive stellar remnants, gravity provides a continuous inward push. Once fusion has stopped, there is no outward thermal pressure to counter it. The system must find resistance elsewhere or continue collapsing. Initially, electron degeneracy pressure provides that resistance, but once electrons are absorbed into nuclei, that resistance disappears. The baton passes to neutrons. Neutrons, like electrons, are fermions. They obey the exclusion principle. They resist being forced into identical quantum states. This resistance manifests as neutron degeneracy pressure, a powerful quantum effect capable of halting collapse in sufficiently small systems. The result is a neutron star, an object where matter exists primarily as a dense assembly of neutrons with a small admixture of protons and electrons. The spacing between particles is comparable to nuclear dimensions. Atomic nuclei, as separate entities, no longer exist. The entire star behaves like a single, gigantic nucleus. This transformation is astonishing, not because it is chaotic, but because it is orderly. At each stage, matter follows clear rules. When one form of resistance fails, another takes over. When electrons can no longer provide pressure, neutrons do. When atomic structure becomes too costly energetically, nuclear structure replaces it. The collapse from atoms to nuclei is not destruction. It is reorganization under constraint. What is especially striking is how little drama accompanies this shift at the microscopic level. There is no moment where atoms shatter violently. Instead, their relevance simply fades. Electrons merge into nuclei. Atomic boundaries dissolve. The system settles into a new equilibrium defined by deeper forces. This quietness can be misleading. The energies involved are immense. The pressures are beyond anything we can produce on Earth. Yet the process itself is smooth, dictated by the requirement to minimize energy under extreme compression. This is a recurring theme when studying extreme conditions. The universe does not behave erratically at its limits. It behaves relentlessly. It follows its rules wherever they lead, even when those rules produce outcomes far removed from everyday experience. Once matter has collapsed into a nuclear-dominated state, many familiar concepts vanish. Temperature becomes less meaningful. Thermal motion is dwarfed by quantum pressure. Chemical reactions are impossible. Even the distinction between solid and liquid loses clarity. Matter exists in a state governed almost entirely by fundamental interactions. Yet even here, collapse is not guaranteed to continue indefinitely. Neutron degeneracy pressure can be sufficient to halt further compression, depending on mass. For a time, matter finds stability again, but that stability is conditional. Add more mass, increase gravitational pressure further, and neutron degeneracy pressure begins to strain. Neutrons are much heavier than electrons, and packing them tightly requires enormous energy. Eventually, the cost becomes unsustainable. The system once again searches for a lower energy configuration. What that configuration is remains uncertain. Theories suggest that neutrons may dissolve into their constituent quarks, forming an even denser state of matter. Quark matter, strange matter, or other exotic phases may appear. Each possibility represents another quiet step downward in structural complexity. Throughout this entire progression, the collapse remains subtle. No single step announces itself loudly. Each transformation is driven by the same simple principle. Under enough pressure, matter gives up complexity in favor of stability. This is why the collapse from atoms to nuclei is so instructive. It shows that structure in the universe is not guaranteed. It exists only because conditions allow it. When pressure removes those conditions, structure retreats gracefully rather than resisting violently. Electrons are remarkably good at holding matter together. They are light, mobile, and governed by quantum rules that make them extraordinarily effective at resisting compression long before anything dramatic happens to the nucleus. In most situations, electrons are the first and strongest line of defense against matter being squeezed too tightly. They shape atoms, define chemistry, and create the familiar solidity of the world around you. As long as electrons have room to maneuver, matter retains its identity. But pressure has a way of asking increasingly difficult questions, and eventually electrons are asked to do something they cannot. At low and moderate pressures, electrons respond flexibly. When atoms are pushed closer together, electrons shift their orbitals. They occupy higher energy states. They spread into shared regions between atoms. This adaptability is why materials can be compressed, stretched, or reshaped without losing their basic nature. Even under enormous pressures by human standards, electrons still manage to arrange themselves in ways that preserve atomic structure. As pressure rises further, this flexibility begins to narrow. Electron states fill up. The number of available low-energy configurations shrinks. Each additional increment of compression requires a disproportionate increase in energy. This is not because electrons are stubborn, but because the rules they follow are absolute. The exclusion principle does not bend. It does not negotiate. Once the available quantum states are occupied, electrons cannot simply squeeze into smaller volumes without consequence. This is where electron degeneracy pressure emerges as a dominant force. It is easy to misunderstand this concept as electrons physically pushing back like compressed springs. In reality, nothing of the sort is happening. Electron degeneracy pressure is a bookkeeping consequence of quantum mechanics. It arises because electrons are forbidden from sharing identical quantum states. When forced into a confined space, they must occupy higher and higher energy states, and that increase in energy manifests as resistance to compression. In white dwarf stars, this resistance is sufficient to counterbalance gravity. The star has no ongoing fusion. There is no outward heat pressure. The entire object is held up by the simple fact that electrons cannot all be placed into the lowest energy states. The result is a stable, incredibly dense object, where matter exists in a state unlike anything found naturally on Earth. At this stage, electrons are already under extreme stress. They are highly relativistic, meaning they move at speeds approaching the speed of light. Their behavior is governed not just by quantum mechanics, but by special relativity as well. Energy and momentum are tightly linked. Small changes in confinement lead to large changes in energy. Yet even this impressive resistance has limits. The problem electrons face is not that they are weak, it is that they are light. Compared to protons and neutrons, electrons have very little mass. As gravity continues to increase pressure, the energy cost of confining electrons rises faster than the energy cost of altering nuclear composition. At some point, the system finds it energetically favourable to remove electrons from the picture rather than compress them further. This is the moment when electrons are forced to give way. Under sufficiently extreme pressure, electrons are driven into atomic nuclei. When an electron encounters a proton under these conditions, a fundamental transformation can occur. The electron combines with the proton to form a neutron, emitting a neutrino in the process. This reaction is known as electron capture, and it represents a profound shift in the nature of matter. The neutrinos produced escape almost immediately. They interact very weakly with matter and carry energy away from the system. This energy loss is crucial. It allows the transformation to proceed without violating conservation laws. What remains is matter, with fewer electrons, fewer protons, and more neutrons. This process does not happen all at once. It unfolds gradually as pressure increases. Regions under the greatest compression undergo electron capture first. As collapse continues, the process spreads. Atomic identity dissolves. Elements lose their distinguishing characteristics. What matters now is not atomic number but density. When electrons are forced to give way, chemistry ends completely. Chemical bonds rely on electrons. Without free electrons to mediate interactions between nuclei, there is no chemistry, no molecules, no materials in the usual sense. Matter becomes nuclear matter. This transition is quiet in a literal sense. There is no sound. There is no explosive release of energy at the site of transformation. But in another sense, it is one of the most dramatic transitions matter can undergo. It marks the end of the atomic era for that material. What replaces electrons as the primary source of resistance is neutron degeneracy pressure. Neutrons, though electrically neutral, obey the same exclusion principle as electrons. They resist being placed into identical quantum states. Because neutrons are much more massive than electrons, the scale of this resistance is different. The distances involved are smaller, the energies are higher, the behaviour of matter becomes dominated by nuclear forces and relativistic effects. When electrons are gone, matter becomes extraordinarily compact. The spacing between particles shrinks to nuclear dimensions. The system is no longer a collection of atoms packed together, but a dense assembly of nucleons pressed into intimate contact. Neutron stars are the most well-studied outcome of this process. They represent a state where electrons have largely given way and neutrons carry the burden of resisting gravity. These objects are astonishingly stable, yet they exist perilously close to further collapse. A small increase in mass can tip the balance. What makes the surrender of electrons so important is that it removes an entire layer of physical description. Electrons are responsible for nearly all macroscopic properties of matter. Electrical conductivity, opacity, elasticity, magnetism, and chemical reactivity all depend on electron behaviour. When electrons are no longer free to act independently, these properties vanish. Matter becomes simpler, but not easier to understand. The physics governing neutron-rich matter is complex and still not fully settled. Interactions between neutrons involve the strong nuclear force, which behaves very differently from electromagnetism. Calculations become difficult. Experimental data is scarce. Much of what we know comes from indirect observation and theoretical modelling. As pressure continues to rise beyond the regime where neutron degeneracy pressure can maintain stability, electrons are long gone and neutrons themselves begin to struggle. At these densities, neutrons may begin to overlap. Their internal structure, composed of quarks, becomes relevant. The idea of a neutron as a distinct particle may lose meaning, just as the idea of an atom did earlier. This progression highlights a recurring pattern. Pressure strips away complexity layer by layer. First molecules lose identity, then atoms, then electrons. Each surrender reveals a deeper, more constrained level of organization. It's important to note that electrons do not disappear entirely in all regions. In neutron stars, a small fraction of electrons remains to maintain charge balance. But they are no longer the architects of structure. Their role is secondary. They exist under conditions where their behavior is tightly constrained by the surrounding nuclear matter. From a broader perspective, the forced surrender of electrons illustrates how pressure reshapes the hierarchy of forces. At low pressure, electromagnetism dominates. At higher pressure, quantum statistics take over. At even higher pressure, nuclear forces and gravity define the system. Each regime has its own logic, its own constraints, and its own limits. The transition away from electrons is also a transition away from familiar intuition. We are accustomed to thinking of matter in terms of atoms and electrons because that is the scale at which our senses operate. When electrons give way, we lose that anchor. Matter becomes something we can only describe mathematically, not visualize directly. Yet this loss of intuition is not a dead end. It is a doorway. By understanding when and why electrons fail, we gain insight into how the universe organizes itself under extreme conditions. We learn which features of matter are contingent and which are fundamental. Neutrons enter the story almost unnoticed. By the time they become the dominant players, so much of familiar physics has already fallen away that their presence can feel almost understated. Chemistry is gone. Atoms are gone. Electrons, once the architects of structure and behaviour, have largely surrendered their role. What remains is matter stripped to something far simpler and far more constrained, and yet even here, the universe still finds a way to resist collapse, at least for a while. Neutron pressure is not something most people ever think about, because under ordinary conditions neutrons rarely exist freely at all. Outside of atomic nuclei, they are unstable, decaying in minutes into protons, electrons, and neutrinos. Inside nuclei, they play a quiet, supporting role, helping hold protons together against their mutual electrical repulsion. They are heavy, neutral, and usually hidden from view. Extreme pressure changes that entirely. When electrons are forced into protons and disappear from the system as independent particles, neutrons take center stage. Matter becomes overwhelmingly neutron-rich. In this environment, neutrons are no longer isolated within nuclei. They form the bulk of the material itself. Their behaviour, dictated by quantum mechanics and nuclear forces, determines whether matter can remain stable or continue collapsing. The resistance provided by neutrons arises from the same fundamental principle that once empowered electrons. Neutrons are fermions. They obey the Pauli exclusion principle. They cannot occupy identical quantum states. When packed together under extreme compression, neutrons are forced into higher and higher energy states, generating neutron degeneracy pressure. This pressure is immense. It can counterbalance gravity in objects far more massive and dense than white dwarfs. Neutron stars, supported primarily by this effect, are among the densest stable objects in the universe. Their internal pressures are so extreme that even describing them stretches language to its limits. Yet despite its strength, neutron pressure operates within a framework that is already beginning to fray. One reason is scale. Neutrons are much heavier than electrons, which means confining them costs energy differently. The distances between neutrons in a neutron star are on the order of femtometers, comparable to the size of the particles themselves. There is very little room left for manoeuvring. Quantum states fill rapidly, energy levels crowd together. Another reason is interaction. Unlike electrons, which primarily interact through electromagnetism, neutrons interact through the strong nuclear force. This force is powerful but short-ranged and complex. It behaves differently depending on distance and configuration. At some separations, it is attractive. At others, it is repulsive. Its behaviour under extreme densities is still not fully understood. As a result, neutron pressure is not as clean or predictable as electron degeneracy pressure. It depends sensitively on how neutrons interact with one another at close range. Different theoretical models predict different behaviours at the highest densities. Some suggest relatively stiff resistance. Others allow for greater compressibility. This uncertainty marks one of the first places where familiar physics truly begins to lose its footing. Up to this point, each stage of increasing pressure has been governed by well-tested principles. Quantum mechanics explains electron behaviour. Nuclear physics explains neutron interactions at moderate densities. General relativity describes gravity accurately in many regimes. But neutron star interiors push all of these theories simultaneously into their limits. At the core of a neutron star, pressures are so high that neutrons may no longer behave as distinct particles. Their internal structure, composed of quarks bound together by gluons, may become relevant. The idea of a neutron as a single, identifiable object may dissolve, just as the idea of an atom dissolved earlier. This is where familiar physics starts to blur, not because it is wrong, but because it is incomplete. Some theories predict that under sufficient pressure, neutrons merge into a sea of deconfined quarks. Instead of neutrons packed together, matter becomes quark matter, where up, down, and possibly strange quarks move more freely in a dense interacting medium. In this state, neutron pressure gives way to quark degeneracy pressure and strong force interactions at an even deeper level. Other models suggest that exotic phases of matter may appear before full quark deconfinement. Hyperons, particles containing strange quarks, may form. Meson condensates may appear. Each of these possibilities represents a new way for matter to reorganize itself under pressure, trading one kind of resistance for another. What unites all of these scenarios is a loss of familiarity. The physics becomes increasingly speculative. Laboratory experiments cannot reproduce these conditions directly. Observational data comes from distant astrophysical objects, interpreted through complex models. Small changes in assumptions can lead to different conclusions. This is a critical shift. Earlier, pressure led to changes that were dramatic but conceptually clean. Atoms collapsed into nuclei. Electrons surrendered to neutrons. Each step followed clearly defined rules. With neutron pressure, we reach a domain where the rules themselves are under debate. Another complication arises from gravity's role. In general relativity, pressure is not just a response to gravity. It contributes to gravity. High pressure increases space-time curvature, enhancing gravitational attraction. This creates a subtle but profound feedback loop. At lower pressures, internal resistance stabilizes objects. At extremely high pressures, that same resistance adds to the gravitational pull trying to crush the object further. Neutron pressure, while resisting compression locally, also deepens the gravitational well globally. This dual role makes stability precarious. A neutron star exists only within a narrow range of masses. Too little mass, and it would not form. Too much, and neutron pressure cannot prevent further collapse. The precise boundary, known as the maximum neutron star mass, depends on details of neutron interactions that remain uncertain. Beyond that boundary, familiar physics offers no firm foothold. According to classical general relativity, collapse would continue toward a singularity, a point of infinite density and pressure, where the equations cease to make sense. But few physicists believe this is the final word. Singularities are widely viewed as signals that a theory has been pushed beyond its domain of applicability. This is where neutron pressure reaches not just its physical limit, but its explanatory limit. At pressures approaching those associated with the Planck scale, space-time itself is expected to behave quantum mechanically. The smooth geometry assumed by general relativity may break down. Quantum fluctuations of space-time may become significant. The concept of a continuous background in which particles exist may no longer apply. Neutron pressure, defined in terms of particles occupying quantum states within space, may simply stop being a meaningful concept. If space is no longer smooth or well-defined, pressure, which relies on areas and volumes, loses its foundation. This does not mean that nothing resists collapse beyond this point. It means that resistance, if it exists, must come from a deeper level of description. Perhaps space-time has its own form of stiffness. Perhaps quantum gravity introduces new constraints that prevent infinite compression. Perhaps collapse proceeds in ways that avoid singularities altogether. At present, these questions remain open. What makes neutron pressure such a pivotal concept is that it represents the last clearly understood form of resistance before physics enters truly unfamiliar territory. Electrons give way cleanly. Neutrons resist strongly, but ambiguously. Beyond them lies a region where our theories overlap imperfectly and our confidence diminishes. This is not a failure of science. It is a natural consequence of pushing inquiry to extremes. The same thing happened when atoms were first probed, when nuclei were discovered, when quantum mechanics emerged. Each time, familiar concepts had to be revised or abandoned. Neutron pressure teaches us something profound about limits. It shows that resistance to compression is not infinite. It depends on the structure of matter and the rules governing its constituents. Once those rules are exhausted, collapse does not stop politely. It searches for new rules. Neutron stars already feel like an endpoint. They compress matter to densities so extreme that language starts to falter, intuition gives up, and familiar categories collapse. By the time matter reaches this state, atoms are gone, electrons have surrendered, and neutrons are packed so tightly that even nuclear physics begins to strain. It would be reasonable to assume that nothing meaningful can exist beyond this point, that further squeezing simply leads to collapse without structure or explanation. And yet gravity does not stop asking its question. When mass continues to accumulate beyond what neutron pressure can support, reality itself is forced into a negotiation. The object is no longer deciding how matter behaves. It is deciding how space and time behave in response to matter that refuses to remain orderly. This is where squeezing reality beyond neutron stars stops being a problem of material science and becomes a problem of space-time. To understand what this means, it helps to pause and remember what has already been lost. Atoms disappeared quietly. Electrons gave way under pressure, absorbed into nuclei. Neutrons took over as the primary carriers of resistance. Each transition stripped away a layer of complexity while exposing a deeper rule. But all of those rules still assumed something fundamental. They assumed that particles exist within space, and that space itself remains a stable arena. Beyond neutron stars, that assumption becomes questionable. Neutron pressure relies on the idea that neutrons occupy quantum states within a volume. It presumes that volume can be defined, that distances have meaning, and that space-time remains smooth enough to support those definitions. As compression increases, those assumptions begin to wobble. Gravity, according to general relativity, is not just a force pulling matter inward. It is the curvature of space-time itself. Mass and energy tell space-time how to curve, and curved space-time tells matter how to move. At everyday scales, this curvature is gentle. At the scale of neutron stars, it becomes severe. Beyond that, it may become extreme enough that space-time ceases to behave as a smooth continuum. This is the critical shift. Beyond neutron stars, squeezing matter is inseparable from squeezing space-time. As gravitational collapse continues, densities rise further. The pressure at the core increases beyond what neutron degeneracy pressure can counter. Neutrons begin to overlap significantly. Their internal structure, composed of quarks bound by gluons, becomes impossible to ignore. The system may transition into phases of matter that have no analogue anywhere else in the universe. One possibility is quark matter. In this state, neutrons dissolve into their constituent quarks, forming a dense sea where quarks move more freely than they do inside individual particles. The strong nuclear force, which normally confines quarks tightly within protons and neutrons, behaves differently under such extreme conditions. Confinement may weaken, boundaries dissolve. This would represent another quiet surrender. Just as atoms lost their identity and neutrons began to blur, particles themselves may lose individuality. Matter becomes something more fluid, less particulate, governed by collective quantum behavior rather than discrete units. Even this may not be the end. As compression continues, energy densities increase dramatically. According to general relativity, energy density contributes to gravity just as mass does. Pressure itself becomes gravitationally significant. The more pressure builds, the more it enhances the curvature of space-time. This creates a feedback loop where compression accelerates its own cause. At some point, classical descriptions break down entirely. general relativity predicts that collapse beyond a certain threshold leads to the formation of a black hole. An event horizon forms, separating a region of space-time from the rest of the universe. Inside this horizon, all paths lead inward. No signal can escape. From the outside, collapse appears to freeze and fade. From the inside, according to classical theory, matter continues collapsing toward a singularity. A singularity is not a physical object in the usual sense. It is a point where the equations predict infinite density, infinite curvature, and infinite pressure. These infinities are not believed to be real. They are signs that the theory has been pushed beyond its domain of validity. This is where squeezing reality becomes literal. At a singularity, space-time itself is compressed beyond any meaningful description. Distances shrink to zero. Time, as a sequence of moments, may cease to exist. Cause and effect lose definition. Pressure, which relies on force applied over area, becomes meaningless because area itself vanishes. Most physicists interpret this not as a description of what truly happens, but as an indication that a deeper theory is required. Quantum mechanics and general relativity, both extraordinarily successful in their own domains, are incompatible under these conditions. Their overlap, known as quantum gravity, remains one of the great unsolved problems of physics. Beyond neutron stars, squeezing reality means entering the regime where quantum gravity must dominate. At the Planck scale, which we are gradually approaching conceptually, space-time is expected to fluctuate violently. Quantum uncertainty applies not just to particles, but to geometry itself. Space may not be continuous. Time may not flow smoothly. The idea of a fixed background dissolves. Some theoretical approaches suggest that space-time is composed of discrete units, much like matter is composed of atoms. In this view, further compression cannot proceed indefinitely. There is a smallest possible volume, a smallest possible length. Once reached, squeezing reality further may be impossible, or may trigger entirely new behavior. Other theories propose that space-time is emergent, arising from more fundamental relationships. Compression in this context might rearrange those relationships rather than shrink distances. What looks like collapse in one description may be reorganization in another. Still, other ideas suggest that collapse could bounce. Instead of forming a singularity, the compressed region might rebound, perhaps creating a new expanding region of space-time. Some speculative models link this idea to the origin of the universe itself, proposing that what we call the Big Bang may have been the outcome of such a bounce. What all of these ideas share is a departure from familiar physics. Beyond neutron stars, we are no longer confident about what the basic ingredients of reality are. Are they particles, fields, loops, strings, networks, or something else entirely? Each proposal attempts to preserve consistency where classical ideas fail. Pressure, in this regime, becomes a signpost rather than a tool. It tells us that something has gone wrong with our descriptions. It tells us that we are asking space and matter to do something they were not designed, or not permitted to do indefinitely. One of the most unsettling implications of squeezing reality beyond neutron stars is that time itself may behave differently. In general relativity, time slows in strong gravitational fields. Near an event horizon, time dilation becomes extreme. From the perspective of a distant observer, processes appear to slow to a halt. Inside the horizon, classical description suggests that time and space swap roles. Movement toward the singularity becomes as inevitable as moving forward in time. Under such conditions, pressure is no longer a process unfolding in time as we understand it. It becomes part of a geometry that no longer distinguishes clearly between before and after. This challenges not just physics, but intuition at a very deep level. We are accustomed to thinking of pressure as something applied gradually over time, with observable consequences. Beyond neutron stars, pressure may be better understood as a static condition of space-time geometry rather than an evolving process. Despite this uncertainty, there are clues. Observations of neutron stars, gravitational waves from mergers, and the behaviour of matter under extreme conditions provide constraints on what is possible. Each new observation narrows the range of viable theories. Each detection of a massive neutron star rules out models that predict early collapse. Each measurement of radius and mass informs our understanding of ultra-dense matter. Even black holes, once thought to be completely inscrutable, are yielding information. Gravitational waves reveal how space-time rings as black holes merge. Event horizon imaging shows shadows consistent with relativistic predictions. These observations do not tell us what happens at the deepest core, but they tell us that our theories are not entirely blind. What remains consistent across all plausible models is this. Beyond neutron stars, squeezing matter inevitably involves squeezing space-time. You cannot separate the two. Pressure is no longer just a property of matter resisting compression. It becomes a property of geometry itself responding to energy and density. This realization reframes the entire journey we have taken so far. Pressure began as a simple idea, force over area. It became a measure of atomic crowding, then a quantum constraint, then a nuclear balancing act. Now it becomes a signal that the structure of reality is being tested. What lies beyond is not simply more density. It is a transformation of the stage on which density is defined. Approaching the Planck scale is not like approaching a place. There is no marker you pass, no boundary you cross where a sign announces that you have arrived somewhere fundamentally new. Instead, it is more like watching familiar tools slowly lose their usefulness. Concepts that once worked well begin to blur, measurements stop behaving politely, equations that once fit the universe neatly start leaving uncomfortable gaps. You can get closer and closer, refining your descriptions, tightening your estimates, but never quite make contact with the thing itself. That is why it makes sense to talk about approaching the Planck scale without touching it. The Planck scale is defined using three constants that sit at the foundation of modern physics. The speed of light, which sets the ultimate limit on how fast information and influence can travel. Planck's constant, which governs the graininess of quantum mechanics and tells us how finely energy and action can be divided. And the gravitational constant, which sets the strength of gravity and the curvature of space-time produced by mass and energy. When these three are combined in specific ways, they produce natural units of length, time, energy, and pressure. These units are not arbitrary. They mark the scale at which gravity and quantum mechanics are expected to become equally important. Below this scale, quantum effects dominate, but gravity is negligible. Above it, gravity shapes space-time smoothly, and quantum fluctuations can often be ignored. The Planck scale is where neither side is willing to step aside. But reaching that scale directly is not something the universe does casually. Even the most extreme environments we know of fall short. The cores of neutron stars, while astonishingly dense, remain orders of magnitude away from Planck densities. Black holes bring us closer, but even there, the region where Planck scale effects would dominate is hidden behind an event horizon, inaccessible to observation and insulated from the rest of the universe. So what does it mean to approach the Planck scale if we cannot reach it? It means examining what happens as we push known physics as far as it will go and watching carefully for signs of strain. It means identifying where assumptions stop being safe. It means noticing when familiar quantities stop behaving independently and begin entangling with one another in unexpected ways. Pressure is one of the clearest indicators of this strain. At lower scales, pressure is a response. Matter is squeezed, and it pushes back. The source of that resistance changes as we move through different regimes, but the concept itself remains intact. There is an area, there is a force, there is a response. As we move closer to Planck scale conditions, even this structure begins to wobble. Pressure depends on the idea that you can define a volume. It assumes that space can be carved into regions with clear boundaries. It assumes that forces act across those regions in a way that can be averaged and described smoothly. These assumptions hold remarkably well across a vast range of conditions, but they are not guaranteed to hold forever. As energy density increases, space-time curvature becomes more pronounced. Distances measured locally no longer agree with distances measured far away. Time flows at different rates depending on location. Even before reaching the Planck scale, general relativity tells us that geometry is dynamic, not fixed. Approaching the Planck scale means approaching a point where geometry itself becomes uncertain. Quantum mechanics introduces uncertainty into every measurement. You cannot know a particle's position and momentum simultaneously with arbitrary precision. At ordinary scales, this uncertainty is small enough to ignore for macroscopic objects. As energies rise and distances shrink, uncertainty becomes unavoidable. When these quantum uncertainties apply not just to particles but to space-time itself, the meaning of distance, area, and volume becomes fuzzy. If you cannot define an area cleanly, pressure loses its footing. You can still talk about energy density, but even that begins to blur as space-time fluctuates. One way to think about this is to imagine trying to measure the surface of a turbulent ocean. At large scales, you can define an average level and talk meaningfully about waves. Zoom in far enough, and the surface becomes chaotic. Spray, foam, droplets, and bubbles make the idea of a smooth surface meaningless. The Planck scale may represent a similar situation for space-time, where the smooth geometry assumed by general relativity breaks down into something more irregular. Approaching this regime does not produce a sudden catastrophe. Instead, familiar descriptions gradually lose precision. Calculations become sensitive to assumptions that once seemed harmless. Small corrections grow larger. Terms that were once negligible refuse to stay quiet. This is why physicists are cautious when extrapolating known equations toward Planck conditions. General relativity predicts singularities when pushed too far. Quantum field theory predicts infinities that must be renormalized away. Both theories give answers that become physically nonsensical if taken literally beyond their tested domains. The Planck scale sits at the intersection of these breakdowns. Approaching it from below, we encounter regions where matter is so dense that pressure rivals energy density. In general relativity, pressure contributes to gravitational attraction just as energy does. This means that increasing pressure increases the tendency for further collapse. The stabilizing role pressure played at lower scales becomes ambiguous. This inversion is subtle. It does not mean that pressure suddenly becomes destructive in all cases. It means that the bookkeeping changes. Pressure is no longer a passive response. It is an active participant in shaping space-time. As we get closer to Planck scale energy densities, the distinction between matter and geometry begins to erode. Energy curves space-time. Curved space-time affects energy distributions. Quantum fluctuations add randomness to both. Trying to separate cause from effect becomes increasingly difficult. Another way to understand this approach is through the limits of measurement. To probe smaller distances, you need higher energies. Higher energies concentrate more mass energy into smaller regions. At some point, the act of measurement itself would create a gravitational disturbance large enough to disrupt what you are trying to measure. This thought experiment suggests a fundamental limit to spatial resolution. You cannot meaningfully probe distances smaller than the Planck length, because doing so would collapse the region into a black hole. This is not a technological limitation, it is a conceptual one. Approaching the Planck scale, then, is also approaching the limits of what can be known operationally. Pressure near this regime becomes less about squeezing matter and more about saturating the informational capacity of space-time. How much energy can be localized in a region before the region ceases to be describable as a region at all? This is not a question classical physics was designed to answer. Various theoretical frameworks attempt to address this. Some approaches suggest that space-time has a discrete structure. Instead of being smooth and continuous, it may be composed of tiny units, woven together in networks or lattices. In such models, further compression cannot shrink space indefinitely. There is a smallest possible unit, and pressure beyond that would not compress space further, but would instead rearrange these fundamental elements. Other approaches propose that spacetime emerges from more abstract entities, such as entanglement patterns or algebraic relationships. In these views, approaching the Planck scale does not mean shrinking space, but changing the way these relationships are organized. Pressure becomes a reconfiguration rather than a compression. There are also approaches that retain continuity but modify the dynamics. In these models, new forces or constraints appear at high energies, preventing singularities and smoothing out collapse. Pressure may trigger these effects, acting as a signal that the system has reached a regime where new rules apply. What all of these ideas share is uncertainty. We do not yet have experimental access to the Planck scale. Particle accelerators, impressive as they are, operate many orders of magnitude below Planck energies. Astrophysical observations provide indirect hints, but they cannot resolve Planck scale structure directly. As a result, much of this territory remains theoretical. This does not make it meaningless. On the contrary, it makes it one of the most carefully studied frontiers in physics. Approaching the Planck scale forces us to confront questions we can usually ignore. What is space made of? Is time fundamental or emergent? Are particles the basic building blocks of reality? Or are they effective descriptions of something deeper? What does it mean for something to have a size or a duration? Pressure, in this context, becomes a lens rather than a mechanism. It reveals when our concepts are being stretched beyond their design limits. It is also important to recognize that approaching the Planck scale does not mean the universe is behaving wildly everywhere. These conditions are localized. They occur in extreme environments, likely confined to regions near singularities or the earliest moments of cosmic history. The rest of the universe remains comfortably far from these extremes. This separation is part of why our theories work so well most of the time. The Planck scale is not a correction you need to apply to everyday physics. It is a boundary that rarely intrudes, and yet its existence matters profoundly. It tells us that there is a limit to compression, a limit to resolution, and possibly a limit to meaning as we currently define it. It tells us that reality has a grain, even if we cannot yet see it clearly. As we approach this limit conceptually, the language we use must become more careful. Words like pressure, density, distance, and time become provisional. They are useful approximations, but not absolute truths. This does not mean they are wrong. It means they are context-dependent. The focus will narrow further onto what happens when these approximations fail completely. What remains when pressure can no longer be defined in the usual way? What happens when spacetime itself resists compression? At first, space, time, and pressure feel like separate ideas. Space is where things are. Time is when things happen. Pressure is what occurs when something is pushed into something else. In everyday life, these concepts rarely interfere with one another. You can measure the pressure in a tire without worrying about time slowing down. You can measure the distance between two objects without wondering whether pressure is quietly reshaping the space between them. Each idea lives in its own mental compartment, tidy and well behaved. As conditions grow more extreme, those compartments begin to leak. The blurring of space, time, and pressure does not happen suddenly. There is no clear threshold where the universe announces that these distinctions no longer apply. Instead, the separation erodes gradually, the way a coastline softens as water slowly eats away at rock. The closer we move toward the most extreme conditions imaginable, the harder it becomes to say where one concept ends and another begins. To understand why this blurring happens, it helps to revisit what space and time really are according to modern physics. In general relativity, space and time are not independent entities. They form a single structure called spacetime. This structure is not rigid. It bends, stretches, and warps in response to mass and energy. Objects do not simply move through space over time. They follow paths determined by spacetime's geometry. Pressure enters this picture in a way that often surprises people. In Newtonian thinking, pressure is a response to gravity. Gravity pulls inward, pressure pushes outward, and balance is achieved. In general relativity, pressure is not merely a response, it contributes to gravity. Energy density curves space-time, and pressure is a form of energy density. This means that pressure itself helps determine how space and time behave. At ordinary pressures, this contribution is negligible. The pressure inside a room does not noticeably curve space-time. The pressure in your body does not alter the passage of time in any measurable way. These effects are so small that they can be safely ignored. At extreme pressures, ignoring them becomes impossible. As pressure increases, its gravitational influence grows. In dense astrophysical objects, pressure adds significantly to space-time curvature. The stronger the pressure, the stronger the curvature. This curvature affects how time flows and how distances are measured. Clocks tick at different rates depending on location. Lengths contract or expand depending on gravitational potential. In these environments, pressure is no longer just a mechanical quantity. It is a geometric one. This is the first sense in which space, time, and pressure begin to blur. Pressure does not merely exist within space and time. It actively reshapes them. As we approach even more extreme regimes, this entanglement deepens. Time dilation becomes severe. Near very strong gravitational fields, time slows dramatically relative to distant observers. In some theoretical descriptions, time may effectively stop at certain boundaries, such as event horizons. From one perspective, processes freeze. From another, they continue inexorably. Pressure under these conditions cannot be described as something changing smoothly over time, because time itself is behaving differently depending on where you stand. A build-up of pressure in one frame of reference may appear frozen in another. The idea of a single, universal timeline breaks down. Space fares no better. In curved space-time, distances are not absolute. The length between 2 points depends on the path you take and the gravitational field you traverse. Under extreme curvature, space can stretch or compress in ways that defy Euclidean intuition. Volumes can shrink or grow without anything moving in the usual sense. Pressure depends on volume. It is defined as force per unit area. If area and volume are no longer stable, pressure becomes ambiguous. You can still calculate it locally, but global descriptions lose coherence. As quantum mechanics enters the picture, the situation grows even stranger. Quantum mechanics tells us that uncertainty is fundamental. You cannot specify all properties of a system with arbitrary precision. At ordinary scales, this uncertainty is tiny compared to the size of objects and the duration of processes. At very small scales and very high energies, uncertainty dominates. When quantum uncertainty applies to space-time itself, the distinction between space and time becomes fuzzy. Fluctuations in geometry mean that distances and durations cannot be sharply defined. The idea of a smooth space-time background dissolves into something more restless. This is often described as quantum foam, not because space literally foams like soap, but because its structure becomes irregular and fluctuating at the smallest scales. In this regime, asking for the exact pressure at a point may be as ill-defined as asking for the exact position of a quantum particle. Pressure assumes stability. It assumes that you can define a region, apply a force, and observe a response. In a fluctuating space-time, regions themselves are uncertain. Forces cannot be cleanly separated from geometry. Response becomes inseparable from cause. Another way this blurring manifests is through the breakdown of locality. In classical physics, interactions occur at specific points in space and time. In quantum physics, especially when entanglement is involved, correlations exist that do not respect simple notions of distance. Under extreme conditions, these non-local effects may become more prominent. If space-time geometry is fluctuating, and quantum correlations span regions that cannot be neatly localized, pressure may not be something that acts at a point or across a surface. It may be a collective property of a region whose boundaries are themselves uncertain. This is not just philosophical discomfort. It has practical consequences for theory. The equations of general relativity treat spacetime as a smooth manifold. The equations of quantum field theory treat particles and fields as existing on that manifold. When the manifold itself becomes quantum, neither framework applies cleanly. Attempts to combine them reveal inconsistencies, infinities, and ambiguities. Pressure sits at the heart of this conflict. It is one of the quantities that appears in both theories, but means something slightly different in each. In relativity, pressure contributes to curvature. In quantum theory, pressure emerges from particle behavior and field interactions. When particles and space-time are no longer separable, pressure inherits that ambiguity. This is why discussions of Planck scale pressure often sound hesitant. Physicists are careful with language because they know they're extending concepts beyond their proven range. They speak of effective pressures, average pressures, or limiting pressures, aware that these are approximations. Even so, approaching this blurred regime teaches us valuable lessons. One lesson is that our everyday distinctions are not fundamental. Space, time, and pressure feel separate because the universe operates far from its limits most of the time. Under ordinary conditions, the interactions between these concepts are weak enough to ignore. That does not mean they were ever truly independent. Another lesson is that limits matter. The fact that these concepts blur suggests that there are natural boundaries to how much compression reality allows, or at least to how we can describe that compression. Whether those boundaries are absolute or emergent remains an open question. It is also worth noting that this blurring does not imply chaos everywhere. It is localized to extreme regimes. Outside of them, space behaves normally, time flows steadily, and pressure is well defined. The universe remains remarkably stable across vast ranges of scale. This coexistence of stability and breakdown is one of the most striking features of modern physics. The same laws that allow you to sit comfortably in a chair also permit black holes to exist. The same space-time that lets GPS satellites function accurately can, under different conditions, stretch and warp beyond recognition. As space, time, and pressure blur, we are reminded that our descriptions are layered. They work because the universe is forgiving at human scales. When that forgiveness runs out, we glimpse the deeper structure beneath. At this stage of the journey, pressure is no longer the central character. It has become a messenger. It tells us when we are approaching a regime where new rules are needed. It signals that the framework supporting our understanding is under strain. The blurring of space, time, and pressure does not give us answers. It gives us boundaries. It tells us where certainty ends and exploration begins. Gravity has always presented itself as the most dependable of forces. It is patient, predictable, and relentless. Drop an object, and it falls. Gather enough mass, and things orbit. Scale it up, and stars form. Galaxies rotate, and clusters arrange themselves in vast, slow patterns. For centuries, gravity felt like the rule maker, the quiet authority that everything else had to obey. Even when other forces behaved strangely, gravity kept doing its job, pulling inward, shaping structure, keeping the universe coherent. For most of physics, gravity played by its own rules, and those rules worked extraordinarily well. Newton's description treated gravity as a force acting instantaneously across space. Einstein replaced that picture with something deeper, showing that gravity is not a force in the usual sense at all, but the curvature of space-time caused by mass and energy. Objects follow paths through this curved geometry, and what we perceive as gravitational attraction is really motion along those paths. This framework has passed every experimental test thrown at it, from the precession of Mercury's orbit to the bending of light around massive objects, to the precise timing corrections required for GPS satellites. In ordinary and even extreme astrophysical situations, general relativity performs beautifully. Neutron stars, black holes, gravitational waves all fit within its predictions. It would be tempting to believe that gravity always knows what it is doing, that it remains self-consistent no matter how far conditions are pushed. Approaching the Planck scale challenges that belief. The reason gravity stops playing by its own rules is not because it suddenly misbehaves, but because the rules themselves were never meant to operate in isolation. General relativity assumes that space-time is smooth and continuous. It assumes that geometry can be defined precisely at every point. It assumes that energy and momentum can be treated as well-defined quantities distributed across that geometry. These assumptions hold remarkably well across enormous ranges of scale, but they are assumptions nonetheless. Quantum mechanics tells a very different story. At small scales, nature is granular. Energy comes in discrete packets, fields fluctuate. Particles do not have definite positions until measured. Uncertainty is not a technical limitation, it is fundamental. Quantum theory works by embracing this uncertainty, not smoothing it away. As long as gravity is weak, these two frameworks can coexist peacefully. Quantum mechanics governs particles and fields. Gravity governs the large-scale structure of space-time. Each stays in its lane. Their interaction is minimal enough that inconsistencies remain hidden. Extreme pressure changes that balance. As pressure increases, energy density rises. In general relativity, energy density directly influences space-time curvature. When energy densities approach extreme levels, space-time curvature becomes severe. Distances shrink. Time dilates dramatically. Eventually, curvature grows so strong that classical descriptions predict singularities, regions where density and curvature become infinite. These infinities are the first sign that gravity's usual rules are failing. In physics, infinities are rarely taken at face value. They are warnings. They tell us that a theory has been pushed beyond where it applies. In electromagnetism, infinities were resolved by quantum mechanics. In fluid dynamics, infinities often signal turbulence or breakdown of assumptions. In gravity, singularities suggest that general relativity is incomplete. What makes this breakdown particularly striking is that gravity is causing its own demise. The stronger gravity becomes, the more it amplifies the conditions that invalidate its own assumptions. Pressure contributes to gravity. Gravity increases pressure. Curvature feeds back on itself. This feedback loop works smoothly until it doesn't. At extreme compression, pressure no longer behaves as a stabilizing response. Instead, it adds to gravitational attraction. This is counterintuitive if you're used to thinking of pressure as something that pushes outward. In general relativity, pressure is part of the stress-energy tensor, the object that tells spacetime how to curve. High pressure deepens curvature just as mass does. In neutron stars, this effect is already significant. The internal pressure contributes meaningfully to the star's gravity. This is one reason neutron stars have strict mass limits. Beyond a certain point, adding mass does not just increase gravitational pull. It increases internal pressure, which further strengthens gravity, pushing the system toward collapse. As compression continues, this effect intensifies. Approaching Planck scale conditions, pressure becomes enormous. Energy densities become extreme. The stress-energy tensor grows without bound. Space-time curvature becomes so severe that the notion of a smooth manifold breaks down. At this point, gravity is still following Einstein's equations, but the equations are producing results that no longer make physical sense. Gravity has not broken its rules. The rules have outlived their usefulness. Another way to see this is through time itself. In strong gravitational fields, time slows relative to distant observers. Near an event horizon, time dilation becomes extreme. From the outside, processes appear to freeze. Inside, according to classical theory, time continues, but the direction of inevitable motion changes. Moving inward becomes as unavoidable as moving forward in time. At a singularity, time as a parameter may cease to exist entirely. Classical equations cannot describe evolution beyond that point. There is no after in the usual sense. Gravity's rules require time to function. When time loses meaning, the rules lose their stage. Quantum mechanics, on the other hand, relies on time in a very different way. Time in quantum theory is typically treated as an external parameter, not something that fluctuates. Particles evolve in time, but time itself is not quantized in the standard framework. This mismatch becomes unavoidable under extreme gravity. When gravity is weak, treating time as a background parameter works fine. When gravity is strong enough to warp time significantly, this treatment becomes inconsistent. When gravity is strong enough to destroy the notion of time entirely, the inconsistency becomes fatal. This is the heart of the problem. Gravity stops playing by its own rules because those rules depend on a background that gravity itself destabilizes under extreme conditions. The stronger gravity becomes, the less valid the assumptions underlying its description. Pressure accelerates this breakdown by pushing systems into regimes where energy densities rival those associated with spacetime itself. At the Planck scale, the energy required to probe small distances is so large that it significantly disturbs spacetime. The act of compression becomes inseparable from the act of altering geometry. In this regime, the separation between matter and gravity collapses. Matter is no longer something that sits in spacetime. It is something that actively reshapes spacetime at every scale. Gravity is no longer a gentle guide of motion. It becomes a dynamic, fluctuating participant in quantum processes. Attempts to quantize gravity, to make it play by quantum rules, reveal how deeply different its nature is. Unlike other forces, gravity couples to everything. There is no way to shield against it. Every form of energy contributes. This universality makes gravity powerful, but it also makes it difficult to tame. In quantum field theories of other forces, interactions can be treated perturbatively. Corrections can be calculated order by order. Gravity resists this approach. When treated as a quantum field, calculations produce uncontrollable infinities. Renormalization techniques that work elsewhere fail. This is another sense in which gravity stops playing by its own rules. It refuses to be treated as just another force. Various approaches to quantum gravity attempt to address this refusal. Some propose that spacetime itself has a discrete structure, preventing infinite compression. Others suggest that gravity is not fundamental, but emergent, arising from more basic quantum degrees of freedom. In these views, the breakdown of gravity's classical rules is not a failure, but a transition to a deeper description. In loop-based approaches, spacetime is quantized into tiny units. Curvature cannot grow without bound because there is a smallest possible area and volume. Collapse may be halted or transformed before singularities form. Gravity's classical rules give way to quantum geometric constraints. In string-based approaches, particles are not point-like but extended objects. At very high energies, strings spread out, softening interactions and preventing infinite curvature. Gravity emerges from vibrational modes of these strings. The classical picture fails because it is an approximation that ignores this extended structure. In emergent gravity ideas, spacetime geometry arises from entanglement patterns or thermodynamic principles. Pressure and curvature are macroscopic descriptions of microscopic information flow. When those descriptions fail, it is because the underlying degrees of freedom are reorganizing in ways that classical geometry cannot capture. All of these approaches agree on one point: gravity's familiar rules are not fundamental at the highest energies. This realization is unsettling because gravity has always felt foundational. It governs the largest structures in the universe. It shapes cosmic evolution. It determines the fate of stars and galaxies. To learn that gravity itself is an approximation feels like removing the ground beneath our feet. But this is also how physics progresses. Electromagnetism once seemed fundamental until it was unified with the weak force. Classical mechanics once seemed absolute until relativity and quantum mechanics revealed its limits. Gravity's turn has simply arrived later, because it is weaker and harder to probe experimentally. Pressure plays a crucial role in forcing this confrontation. Without extreme pressure, gravity remains well behaved. With it, gravity is pushed into regimes where its classical description fails. Pressure is the lever that exposes gravity's seams. It is important to emphasize that gravity does not stop working in these regimes. Planets do not suddenly drift apart. Black holes do not evaporate spontaneously. What stops working is our ability to describe gravity using the same equations that worked before. This distinction matters. Nature remains consistent. Our models do not. As pressure increases toward Planck levels, gravity becomes entangled with quantum uncertainty. Fluctuations in energy lead to fluctuations in curvature. Space-time becomes noisy. The smooth trajectories of classical motion dissolve into probabilistic histories. The idea of a single, well-defined geometry becomes an approximation. In such a world, gravity cannot enforce its own rules because the rules depend on stability that no longer exists. Geometry fluctuates too much. Time refuses to behave as a simple parameter. Pressure loses its classical meaning. And yet, this breakdown is not an ending. It is an invitation to reimagine gravity not as a force or a curvature, but as something deeper. Perhaps it is a statistical effect. Perhaps it is an emergent property of quantum entanglement. Perhaps it is a manifestation of information constraints. Whatever the answer, it will have to explain why gravity behaves so predictably at large scales and so strangely at extreme ones. It will have to explain why pressure both resists and enhances collapse. It will have to explain how space-time can be both smooth and granular, depending on context. When compression reaches the point where gravity has exhausted its familiar rules and space-time itself begins to strain, the picture of reality changes in a subtle but profound way. Up to now, pressure has always acted on something. It squeezed atoms, then electrons, then neutrons, and eventually even challenged space-time's smooth geometry. But there comes a regime where it is no longer clear what exactly is being compressed. This is where compression meets what physicists often call quantum foam, and where the idea of a stable background dissolves into something restless, uncertain, and deeply unfamiliar. Quantum foam is not a material. It is not a substance bubbling beneath reality. It is a metaphor, imperfect but useful, for what space-time may look like at extremely small scales when quantum effects dominate. The phrase was introduced to describe a situation where space-time is no longer smooth and continuous, but fluctuates wildly due to quantum uncertainty. At these scales, geometry itself is unstable, distances jitter, durations flicker. The very notion of a fixed point in space or a precise moment in time loses clarity. To understand why compression would ever encounter such a regime, it helps to recall how deeply compression depends on geometry. Pressure assumes volume. It assumes that space can be divided, measured, and reduced. It assumes that matter occupies regions that can be squeezed smaller and smaller. All of this relies on space-time behaving politely, offering a consistent stage on which physical processes unfold. Quantum foam challenges that stage. According to quantum mechanics, uncertainty is unavoidable. You cannot measure everything precisely at once. Normally, this uncertainty applies to particles and fields within space-time. Space-time itself is treated as a passive background. As we approach the Planck scale, this separation becomes impossible to maintain. The energy densities required to probe very small distances are so large that they significantly disturb space-time itself. The act of compression becomes inseparable from the act of measurement. Imagine trying to compress a region of space to an extremely small size. To do so, you must concentrate energy into that region. Energy has mass equivalence. Mass curves space-time. As you add energy, space-time responds by curving more strongly. At some point, the curvature becomes so intense that space-time cannot remain smooth. Quantum fluctuations in geometry become unavoidable. This is where quantum foam enters the picture. Instead of a smooth fabric, space-time becomes a restless structure where tiny regions are constantly fluctuating. Wormhole-like connections may briefly form and vanish. The distinction between neighbouring points becomes ambiguous. The concept of here and there loses sharpness. These fluctuations are not large-scale distortions you could observe directly. They occur at scales far smaller than anything accessible to current experiments. When compression meets this foam-like regime, pressure can no longer behave in its usual way. Pressure relies on averaging behavior over many particles and over well-defined regions of space. In a fluctuating spacetime, there is nothing stable to average over. The region you are compressing is not a fixed entity. Its size, shape, and connectivity fluctuate. Applying force to such a region does not produce a clean, predictable response. This does not mean that compression becomes meaningless. It means that the language we use to describe it must change. One of the first consequences is that locality begins to weaken. In classical physics, causes have effects at specific locations. Pressure at a point influences nearby regions. In quantum foam, the notion of nearby becomes fuzzy. Tiny space-time connections may briefly link regions that would otherwise be distant. Compression in one area could influence geometry in unexpected ways elsewhere. Another consequence is that energy and geometry become deeply entangled. In classical descriptions, you can often separate matter from the space it occupies. In the quantum foam regime, this separation fails. Energy fluctuations create geometric fluctuations, which in turn affect how energy can be localized. Compression becomes a feedback process involving both matter and space-time. At this stage, it is no longer accurate to say that pressure is squeezing matter within space. Pressure is acting on the structure of space-time itself. Some theoretical approaches suggest that space-time at these scales is composed of discrete elements. Instead of being continuous, it may consist of tiny units with minimum sizes. If this is the case, compression encounters a fundamental limit. You cannot shrink space beyond its smallest unit. Applying more pressure does not reduce volume further. Instead, it rearranges the underlying structure. In such models, quantum foam is not chaos, but a kind of granular order. The fluctuations arise because these discrete elements are constantly reconfiguring. Compression may push the system into new configurations, but it cannot eliminate the fundamental graininess. Pressure becomes a driver of reorganization rather than collapse. Other approaches view quantum foam as a manifestation of deeper degrees of freedom. Space-time may emerge from more fundamental entities such as entanglement relationships. In this view, compression does not act on space directly. It alters patterns of entanglement. What looks like geometric fluctuation is really a change in how information is distributed. In these frameworks, pressure becomes an informational concept. It measures how densely information is packed, rather than how tightly matter is squeezed. When information density reaches a certain limit, further compression is prohibited or redirected. This idea is closely related to concepts like entropy bounds and holography, which suggest that the amount of information in a region scales with its surface area rather than its volume. If these ideas are correct, quantum foam represents the regime where information density saturates. Compression beyond this point cannot increase density in the usual way. The system responds by altering geometry, connectivity, or even dimensionality. Another striking possibility is that quantum foam provides a natural mechanism to avoid singularities. Classical general relativity predicts infinite densities under extreme collapse. Quantum fluctuations may intervene, preventing geometry from collapsing to a point. Instead of a singularity, compression might produce a region of intense but finite curvature, constantly fluctuating rather than diverging. This would mean that the universe has a built-in safety valve. Compression can push space-time to its limits, but not beyond them. The foam-like behavior absorbs the stress, redistributing it across fluctuating geometries. It is important to emphasize that these ideas remain speculative. We do not yet have a complete theory of quantum gravity. Quantum foam is a placeholder for phenomena we suspect exist but cannot yet describe precisely. Still, the consistency of these ideas across different approaches suggests that something like this behavior may be unavoidable. When compression meets quantum foam, the notion of scale itself becomes ambiguous. At ordinary scales, smaller means more detailed. At Planck scale conditions, smaller may not mean anything at all. Zooming in reveals not clarity but complexity. There is no smooth structure to resolve, only fluctuation. This has profound implications for the idea of pressure. Pressure traditionally increases as volume decreases. If volume cannot decrease meaningfully beyond a certain point, pressure loses its monotonic relationship with compression. Applying more force does not necessarily produce a smaller region. It may produce more violent fluctuations instead. In this sense, pressure becomes self-limiting. Another implication concerns time. Quantum foam does not just affect space. Time intervals may fluctuate as well. The order of events may become ambiguous at very small scales. If time itself fluctuates, describing compression as a process unfolding over time becomes problematic. Pressure may not build smoothly. It may exist as a condition rather than a sequence. This challenges deeply ingrained intuitions. We're used to thinking of processes as happening step by step. In the foam-like regime, the notion of steps may break down. Compression may not be something that happens. It may be something that is. Despite these difficulties, approaching this regime teaches us something important. It shows that the universe resists infinite compression, not necessarily by brute force, but by undermining the assumptions that make compression meaningful. Space stops being smooth, time stops being uniform, pressure stops being well-defined. The meeting of compression and quantum foam is not a dramatic collision. It is a quiet erosion of concepts. Familiar tools stop working, new ones are required. What makes this especially intriguing is that similar ideas appear in different corners of theoretical physics. Black hole thermodynamics, holographic principles, loop-based approaches, and string-based models all hint at limits to localization and compression. They differ in details but converge on the idea that spacetime has a finite capacity for structure. Compression, in this context, is a way of probing that capacity. Pressure has followed us faithfully through every stage of this journey. It began as a simple idea, force spread over area, something you could feel with your hands or notice in your ears as altitude changed. As conditions grew more extreme, pressure transformed from a practical concept into a diagnostic one, revealing how matter responds when space becomes scarce. It stripped away molecules, then atoms, then electrons, then even the comfortable idea of neutrons as solid building blocks. Eventually, pressure stopped acting only on matter and began acting on space-time itself. Now we arrive at the most difficult question of all. When we approach the Planck scale, when space-time fluctuates, geometry becomes uncertain, and quantum effects refuse to stay confined. Does pressure still mean anything at all? This is not a trick question, and it is not merely philosophical. It cuts directly to the heart of how physics defines reality. Pressure is not just a number we calculate, it is a concept built on assumptions. It assumes that space can be divided into regions. It assumes that forces act across surfaces. It assumes that those surfaces exist in a stable way over time. At the Planck scale, every one of those assumptions is under threat. To see why, it helps to revisit what pressure actually requires in order to exist as a meaningful quantity. Pressure depends on area depends on distance depends on space-time geometry. If geometry is smooth and well-defined, pressure makes sense. If geometry fluctuates, fragments, or becomes discrete in unfamiliar ways, pressure begins to lose its footing. At everyday scales, we rarely think about this dependency. Space feels solid and reliable. You can mark off a square meter on the floor, apply a force, and compute a pressure. Even in extreme astrophysical environments like neutron stars, physicists can still define pressure locally. Space-time is curved, but it is smooth enough that concepts like volume and area remain usable. The Planck scale is different. At this scale, quantum uncertainty is no longer confined to particles or fields. It applies to space-time itself. Distances fluctuate. Areas cannot be pinned down precisely. time intervals jitter. The very fabric on which pressure is defined becomes restless. If you cannot define an area sharply, you cannot define pressure sharply either. This immediately raises a problem. Pressure is not a fundamental quantity in the same way that energy or charge might be. It is an emergent quantity. It arises from averaging the behavior of many degrees of freedom over a region of space. It works because those degrees of freedom are numerous, and the region is large compared to their characteristic scales. At the Planck scale, there is no large compared to. Everything is at the characteristic scale. This suggests that pressure, as we usually understand it, may simply stop existing at this limit, not because the universe becomes empty or featureless, but because the concept no longer applies. It would be like asking for the temperature of a single molecule. The question is not wrong, but it is misplaced. Temperature emerges from many particles. Pressure does the same. However, this is not the end of the story. Even if classical pressure ceases to be meaningful, something else may take its place. The universe does not stop responding to compression simply because our language fails. The question becomes what form that response takes, and whether it can still be described in pressure-like terms. One clue comes from the way Planck units are constructed. Planck pressure can be defined mathematically using fundamental constants. It represents an energy density so high that quantum gravitational effects dominate. This suggests that there is a natural scale at which our usual descriptions transition into something else. The existence of a Planck pressure hints that the universe recognizes a limit, even if the way it enforces that limit is unfamiliar. But defining a number is not the same as defining a concept. Planck pressure does not necessarily correspond to a measurable pressure in the traditional sense. It is not something you could apply with a piston or contain within a vessel. It is a scale at which the assumptions behind pressure break down. The number exists as a warning label rather than a physical setting. Another way to approach this question is to ask whether force still exists at the Planck scale. Pressure is force distributed over area. If area is ill-defined, perhaps force itself becomes ambiguous. In quantum gravity, interactions may not occur through forces acting across space in the classical sense. They may be encoded in relationships, constraints, or correlations that do not resemble pushes or pulls. If this is the case, pressure may dissolve into something more abstract, like a constraint on information density or a limit on entanglement. Instead of asking how hard something's being squeezed, the relevant question may become how much information can be packed into a region before spacetime reorganizes itself. This idea appears in several theoretical frameworks. In holographic descriptions, the maximum information content of a region scales with its surface area rather than its volume. This suggests a fundamental limit on compression. Beyond a certain point, adding more energy does not increase the number of degrees of freedom inside a region. Instead, it changes the region's boundary or geometry. In such a picture, pressure is not eliminated but reinterpreted. It becomes a signal that information density is approaching saturation. When that happens, the system responds not by compressing further, but by altering its geometric or informational structure. This is a very different role from the one pressure plays in everyday physics. Another perspective comes from thermodynamic approaches to gravity. Some physicists have suggested that gravity itself may be an emergent phenomenon, arising from statistical behavior of microscopic degrees of freedom. In these views, spacetime has entropy and temperature, and gravitational dynamics emerge from thermodynamic principles. If gravity is emergent in this way, pressure may also be emergent. It would not exist at the deepest level of description, but only appear when many underlying degrees of freedom behave collectively. At the Planck scale, where those degrees of freedom are not yet organized into space-time as we know it, pressure would have no meaning. This aligns with the idea that Planck-scale physics is not about smaller versions of familiar things, but about entirely different kinds of entities. Trying to apply classical pressure to that regime may be like trying to apply traffic laws to individual molecules of air. There is also the question of time. Pressure is usually something that changes over time. It builds, relaxes, fluctuates. If time itself becomes ill-defined or behaves non-classically at the Planck scale, describing pressure as a time-dependent quantity may not make sense. Pressure may exist only as a static constraint or a boundary condition, not as a process. In some approaches to quantum gravity, time does not appear as a fundamental variable at all. Instead, it emerges from correlations between other quantities. In such a framework, pressure cannot be something that evolves in time in the usual sense. It would have to be described relationally, if at all. This leads to a subtle but important point. When we ask whether pressure still means anything at the Planck scale, we are really asking whether our way of carving reality into concepts survives at that depth. Pressure is one of those concepts. It works because the universe, at most scales, allows us to separate space, time, matter, and force cleanly enough. At the Planck scale, that separation collapses. Space is no longer just a container. Time is no longer just a parameter. Matter is no longer just particles. Force is no longer just interaction. Everything becomes entangled, literally and conceptually. Pressure, which relies on those separations, cannot remain intact. And yet, it would be misleading to say that nothing replaces it. Whatever the ultimate theory of quantum gravity turns out to be, it will have to explain why compression is limited. It will have to explain why infinite densities do not appear in nature, or why they are hidden behind horizons, or why they are resolved by new physics. It will have to explain why spacetime resists being crumpled beyond a certain point. That resistance may not look like pressure, but it plays an analogous role. Instead of force per area, it may be a limit on curvature. Instead of stress, it may be a constraint on entanglement. Instead of mechanical resistance, it may be a topological property of spacetime. But the function is similar. Something pushes back against unlimited compression. From this perspective, pressure at the Planck scale is not gone. It has been generalized beyond recognition. This helps explain why physicists continue to talk about Planck pressure, even while acknowledging its conceptual limitations. The term survives because it points toward a real physical issue. How does the universe respond when pushed to its limits? What prevents arbitrary compression? What enforces consistency when classical descriptions fail? Pressure, stripped of its everyday meaning, becomes shorthand for these deeper questions. It is also worth noting that we may never be able to observe Planck-scale pressure directly. These regimes are hidden behind horizons or confined to the earliest moments of cosmic history. Our access will likely remain indirect, mediated through observations of black holes, gravitational waves, and the large-scale structure of the universe. This makes conceptual clarity even more important. We must be careful not to mistake mathematical artifacts for physical realities or familiar words for fundamental truths. At this point in the journey, pressure has done its job. It has guided us from the familiar to the unfamiliar. It has revealed the layers of resistance that structure matter and space-time. It has led us to the edge of meaning itself. Whether pressure still means something at the Planck scale depends on what we mean by meaning. As a classical quantity, it likely does not survive. As a signpost pointing toward limits, constraints, and transitions, it remains invaluable. If pressure dissolves at the deepest level, what takes its place? What kind of structure, if any, exists beyond the point where compression loses its conventional meaning? When compression reaches its absolute extreme, when every familiar form of resistance has been tested and found wanting, we're left with a strange silence. Not an absence of activity, but an absence of clear description. Pressure has faded as a useful word. Geometry has stopped behaving smoothly. Time no longer offers a reliable sequence of before and after, and yet something remains. The universe does not simply vanish when pushed to its limits, it does something else instead. The question is what? Maximum compression is not defined by a particular object or location. It is defined by a condition, a situation in which the known rules of physics can no longer tell a complete story. In classical general relativity, This condition appears as a singularity. Density becomes infinite. Curvature diverges. Equations stop producing meaningful answers. But singularities are widely understood not as physical endpoints, but as placeholders for ignorance. They mark where a theory has reached beyond what it can responsibly describe. So when we ask what the universe might be hiding at maximum compression, we are really asking what replaces singularities once a deeper description takes over. One possibility is that the universe hides nothing dramatic at all, at least not in the way imagination tends to expect. Instead of a violent endpoint, maximum compression may correspond to a state of extreme but finite density, regulated by quantum gravitational effects. In this view, the universe quietly refuses to be compressed beyond a certain limit, not because of an explosion or a rebound, but because the structure of spacetime itself cannot accommodate further reduction. This idea appears in several approaches to quantum gravity. In these frameworks, spacetime is not infinitely divisible. There is a smallest meaningful unit of length, area, or volume. Compression can approach this scale, but not surpass it. When matter and energy are forced into a region this small, the geometry resists further change, not through force, but through limitation. If spacetime has a minimum granularity, then maximum compression corresponds to filling that granularity completely. There is no room left, not in the metaphorical sense, but in the literal sense of available degrees of freedom. Adding more energy does not shrink the region further, it alters its internal state instead. In this scenario, what the universe hides at maximum compression is not a singular point, but a saturated structure. Everything that can exist within that region already does. There is no additional capacity for localization. Compression has reached a ceiling. Another possibility is that maximum compression reveals that spacetime itself is not fundamental. Instead of being a thing that can be squeezed, spacetime may emerge from more basic relationships. In these views, compression does not act on space directly. It acts on the underlying degrees of freedom that give rise to space. What might those degrees of freedom be? Different theories offer different answers. Some propose networks of connections, where nodes and links encode adjacency and interaction. Others propose extended objects whose vibrational modes give rise to particles and geometry. Still others propose that spacetime emerges from patterns of quantum entanglement. If spacetime is emergent, then maximum compression corresponds to a state where these underlying relationships are maximally packed, or maximally entangled. Space, as we understand it, may cease to exist in any familiar form. What remains is a highly constrained configuration of whatever the true fundamental entities are. In this picture, the universe hides a different kind of order at maximum compression. Not the order of geometry or particles, but the order of information. Information has become an increasingly important concept in modern physics. Black hole thermodynamics, for example, suggests that the information content of a region is limited by its surface area, not its volume. This implies a fundamental bound on how much information can be packed into a given region of space-time. At maximum compression, this bound may be saturated. If so, the universe hides a state where information density is at its maximum possible value. No additional information can be encoded locally. Any attempt to add more energy or complexity must manifest as a change in global structure, rather than further localization. This perspective reframes compression entirely. Instead of thinking in terms of matter being squeezed, we think in terms of information being packed. Pressure becomes an indirect measure of informational saturation. When saturation is reached, the response is not further compression, but reorganization. What might that reorganization look like? One possibility is that it produces horizons. Event horizons already play this role in black hole physics. They limit access to information. They separate regions of space-time in a way that preserves consistency. Maximum compression may naturally produce horizon-like structures that prevent further localization. Another possibility is that maximum compression leads to phase transitions in space-time itself. Just as matter undergoes phase transitions when temperature or pressure crosses certain thresholds, spacetime may undergo transitions when energy density reaches critical values. These transitions may change the effective dimensionality of spacetime, its connectivity, or its causal structure. Some theories suggest that spacetime may behave as if it has fewer dimensions at very small scales. At large scales, space appears three-dimensional. At extreme compression, it may effectively become two-dimensional, or even one-dimensional. This dimensional reduction could act as a release valve, altering how compression manifests without requiring infinite density. If dimensionality changes, then maximum compression does not look like an endpoint. It looks like a transformation. Another intriguing possibility is that maximum compression hides a kind of bounce. Instead of collapse continuing indefinitely, the system may reach a state where further compression becomes dynamically impossible. At that point, the system may expand instead. This idea appears in certain cosmological models, where the Big Bang is not the beginning of time, but the aftermath of a previous contraction. In such models, maximum compression is not a singularity, but a turning point. Time does not end. It changes direction or redefines itself. The universe transitions from contraction to expansion through a phase governed by quantum gravitational effects. What makes this idea compelling is that it offers a way to avoid infinities while preserving causal structure. Compression reaches a maximum. Geometry fluctuates violently. Classical descriptions fail. But the system remains finite and evolves into a new phase. If this is correct, what the universe hides at maximum compression is not destruction, but continuity. There is also the possibility that maximum compression hides nothing that can be described at all using our current conceptual tools. The ultimate state may be so alien that language rooted in space, time, and matter simply cannot apply. This does not mean the state is meaningless. It means our categories are insufficient. We have encountered this before in physics. Classical concepts failed at atomic scales. New language was required. Particle trajectories gave way to wave functions and probabilities. Determinism gave way to uncertainty. The failure of old concepts did not imply chaos. It implied deeper order. Maximum compression may represent another such boundary. At that boundary, the universe may be hiding a description that does not involve objects in space, evolving over time, but something more abstract. Perhaps a static structure that contains all possible configurations. Perhaps a network of relations that encode consistency rather than motion. Perhaps a mathematical object that does not privilege time or space as fundamental. This idea aligns with certain interpretations of quantum gravity in which the universe is fundamentally timeless. In these views, time emerges only at lower energies as an effective description. At maximum compression, time may dissolve, leaving behind a timeless structure. If time dissolves, compression itself must be reinterpreted. Compression is normally a process, something that happens over time. In a timeless description, compression may be a relation between configurations rather than a sequence of events. Maximum compression would not be something reached, it would be something defined. Another aspect to consider is that maximum compression may not be unique. Different initial conditions, symmetries, or quantum states may lead to different maximal configurations. The universe may hide not a single ultimate state, but a family of them. This opens the door to a richer picture. Instead of one endpoint, there may be many consistent ways for reality to exist at its limits. The particular configuration realized in any given situation would depend on global constraints, boundary conditions, and quantum probabilities. In this sense, maximum compression might resemble the space of possible ground states in quantum systems. There is not one ground state, but many, related by symmetry or topology. The universe hides not an answer, but a landscape. It is also worth considering the role of observation. Much of what we think we know about extreme compression comes from extrapolation. We cannot directly observe Planck scale phenomena. We infer their existence by pushing theories beyond tested domains. This means that some features of what we imagine at maximum compression may be artifacts of our descriptions rather than reflections of reality. The universe may be hiding simplicity where we expect complexity, or stability where we expect chaos. It may be hiding constraints so strong that many possibilities we imagine are simply forbidden. This idea resonates with a recurring theme in physics. The deeper we probe, the fewer options remain. Fundamental laws are often simpler, not more complicated than emergent phenomena. Maximum compression may hide an extreme simplicity, a state defined by very few parameters, with everything else stripped away. What makes all of this especially striking is that maximum compression is not something the universe seeks casually. It appears only under extraordinary circumstances. It is hidden behind horizons, confined to the earliest moments of cosmic history, or sequestered in regions we cannot access directly. This suggests that whatever is hidden there is not meant to interact freely with the rest of the universe. This seclusion may be essential. If maximum compression were easily accessible, the universe might be unstable. By hiding its deeper structure behind limits, the universe preserves the conditions necessary for complexity, structure, and life elsewhere. In this way, maximum compression plays a quiet but crucial role. It defines the boundaries of possibility. It enforces consistency. It prevents runaway behavior. It acts as a silent guardian of physical law. As we approach the end of this exploration, it becomes clear that the question is not whether the universe hides something at maximum compression, but what kind of hiding is taking place. Is it hiding a finite structure, a new phase, a timeless description, an informational limit, or simply the inadequacy of our current language? The honest answer is that we do not yet know. What we do know is that pressure has carried us as far as it can. It has guided us from familiar sensations to the edge of conceptual meaning. Beyond this point, pressure dissolves into deeper ideas about structure, information, and consistency. After wandering so far from familiar ground, it can feel strange to return. We've followed pressure beyond cushions and oceans, past stars and collapsed matter, all the way to the edge where even space and time hesitate to behave. We've spoken about limits that are not just physical but conceptual, places where language softens and certainty loosens its grip. And now, gently, without snapping back or drawing a hard line, it's time to let the scale widen again, to drift outward from those extremes and settle back into something recognizably human. This return is not a reversal. Nothing we explored vanishes as we come back. The universe does not forget its deepest rules when we stop looking at them. Instead, those rules recede into the background, quietly supporting everything we take for granted. The same laws that strain and blur under maximum compression are the ones that allow a floor to feel solid beneath your feet, a chair to hold your weight, and air to rest invisibly around you without crushing or dispersing. At human scale, pressure behaves politely again. It resumes its role as a practical quantity. Weather maps track it. Engineers design around it. Doctors measure it. You feel it change when you yawn on an airplane or dive beneath the surface of a pool. There is nothing mysterious about it here, and that is precisely what makes this scale so remarkable. The universe is operating far from its limits, in a regime where everything has room. That room is not accidental. The fact that we live so comfortably distant from maximum compression is one of the quiet conditions that makes everyday existence possible. If spacetime were always on the brink of its deepest limits, nothing stable could form. Atoms would not persist. Chemistry would not unfold patiently. Planets would not maintain gentle orbits. Life, which depends on long chains of cause and effect unfolding reliably over time, would have no foothold. Instead, the universe offers an enormous buffer. Between the pressures that dissolve atoms and the pressures you experience leaning against a pillow, there is an almost unimaginable span. That span is where structure thrives. It is where complexity accumulates. It is where slow processes are allowed to complete themselves without interruption. This is easy to miss because we're used to thinking of extremes as defining reality. Black holes, singularities, Planck scales. These ideas capture attention precisely because they sit at the boundaries. But boundaries do not describe the whole space. Most of the universe lives comfortably away from them. Most of the universe is calm. Your body, right now, is an example of this calm. Inside you, pressures vary, blood moves, lungs expand and contract. Cells maintain delicate balances across membranes. All of this depends on pressure behaving in predictable ways. It depends on space being stable, time flowing smoothly, and forces remaining well behaved. None of it would function if the deeper, more extreme rules were intruding directly. And yet, those deeper rules are still there. The same quantum principles that become overwhelming at extreme compression are quietly at work in every atom of your body. The same space-time geometry that warps violently near black holes is gently curved beneath your feet by the mass of the Earth. The same limits that prevent infinite compression are what make solidity possible at all. This layered nature of reality is one of its most reassuring features. The universe does not require you to engage with its deepest complexities in order to exist within it. It handles those complexities on your behalf. It keeps its most demanding negotiations confined to places and conditions where they do not disrupt the broader order. That order expresses itself in rhythms. Day follows night. Seasons shift. The planet rotates with dependable steadiness. Pressure gradients in the atmosphere generate winds that move heat around the globe. Oceans circulate. Weather forms and dissipates. None of this requires Planck-scale physics to be consulted moment by moment. It all works because the universe is operating in a regime where its deepest limits are far away. There is something quietly comforting about that. We often imagine that understanding the universe means chasing its extremes, pushing toward its sharpest edges. There is value in that pursuit. It reveals the constraints that shape everything else. But understanding also means appreciating where we are positioned within that vast range. We exist in a region that is forgiving, spacious, and remarkably stable. Pressure, once again, becomes something you can feel without fear. You can press your hand against a surface and trust that it will respond predictably. You can lie down and let gravity and pressure distribute your weight evenly, allowing muscles to relax. You can breathe without thinking about the fact that air molecules are colliding with you constantly, exerting pressure that you have evolved to match perfectly. This matching is important. Life exists not just because pressure is present, but because internal and external pressures are balanced. Cells maintain internal pressure against their surroundings. Blood pressure is regulated carefully. Even at a psychological level, we talk about pressure as something that can be managed, adjusted, eased. There is a quiet parallel here. Just as matter breaks down when pressure becomes too extreme, so do systems at the human scale. Structures fail when forces exceed their design limits. Bodies struggle when internal balances are pushed too far. Minds tire when demands accumulate without relief. The universe, it seems, favors moderation not just in physics, but in the conditions that allow complexity to persist. Returning to human scale also returns us to time as we normally experience it. Time no longer stretches or fragments. It resumes its steady pace. Minutes feel like minutes again. Thoughts unfold in sequence. There is a before and an after that makes sense. That sense of sequence is something we rely on deeply, especially as we prepare for rest. Sleep itself depends on time behaving reliably. Hormones shift gradually. Brain activity slows. Awareness softens. None of this would work in a universe where time behaved erratically at all scales. Instead, The universe gives us a long, gentle corridor between its extremes and our experience. As you settle into that corridor, it can be helpful to remember that nothing we discussed earlier is pressing in on you now. Maximum compression is not lurking beneath the floor. Quantum foam is not bubbling up through the walls. Gravity is not about to forget its manners. The conditions around you are stable, well within the range where reality behaves kindly. This does not make the deeper questions irrelevant. It gives them context. The fact that there are limits to compression does not make everyday pressure meaningless. It makes it meaningful by contrast. The fact that space and time can blur does not undermine their reliability here. It highlights how special this regime is. The fact that gravity has rules it eventually outgrows does not make it untrustworthy. It makes its everyday consistency more impressive. There is a tendency to think that knowing about extremes should make the ordinary feel fragile. In many ways, it does the opposite. It shows how carefully structured the universe is, how many layers of constraint protect the conditions we rely on. Even now, as you rest, gravity is holding you gently in place. Pressure is distributing your weight evenly. Air is supporting your breathing. Space-time is behaving smoothly enough that you do not have to notice it at all. These are not trivial achievements. They are the result of a universe that has rules, limits, and boundaries, and that respects them most of the time. As thoughts begin to slow, it's natural for the mind to wander back over what it has heard. Ideas about collapse, limits, and hidden structures may drift through awareness. There is no need to hold on to them tightly. They can pass by without effort. You do not need to resolve them tonight. The universe is not asking you to solve its deepest problems in order to sleep. If anything, those problems are reminders that the universe can take care of itself. Maximum compression, Planck scales, quantum foam, these are all places where reality manages its own constraints. They are not burdens placed on you. They are safeguards built into existence itself. Knowing they exist can be oddly reassuring. It means there are boundaries. It means things do not spiral endlessly out of control. So as attention returns fully to the present moment, to the simple fact of being here, it may help to notice the absence of pressure rather than its presence. Notice the ease with which your body is supported. Notice the steadiness of your breathing. Notice how thoughts can slow without resistance. The universe is vast, but it has made room for this moment. Wherever you are listening from, whatever time it happens to be in your part of the world, this moment is operating comfortably within the universe's most forgiving range. Nothing is being pushed to its limits. Nothing is being asked to collapse or resist impossibly large forces. Everything is allowed to remain as it is, and that is enough. As this exploration draws gently back to rest, there is no need for a sharp ending. The ideas we've moved through do not require closure. They can remain open, quietly present, like distant stars that do not demand attention once you stop looking directly at them. If you feel sleep approaching, you can let it arrive without effort. The universe has already done the hard work of setting the conditions. All that remains is to allow yourself to drift within them, supported by the same stable laws that govern everything from atoms to galaxies. There will always be deeper questions. There will always be extremes beyond reach. Tonight does not belong to them. It belongs to this scale, this balance, this calm. And so, without concluding anything that needs to be concluded, without drawing a firm line or sealing a final thought, it's enough to rest here for now, carried gently by a universe that knows both its limits and how to stay comfortably far from them when it matters most.